Hello there, and welcome to Science for Sleep, where curiosity drifts in slowly like starlight, and science finds a softer voice at the edge of your day. Tonight we're going to wander together into one of the most astonishing frontiers of human exploration, a place so far removed from ordinary life that it can feel almost unreal. You've heard of telescopes before, of course. They sit in observatories or orbit the Earth, collecting light from planets and stars. But the one we're speaking of tonight is something altogether different. It is a window not just into distance, but into time itself. The James Webb Space Telescope, launched in the quiet darkness of December 2021, is not only peering deeper into the cosmos than any machine before it, but it is also tugging at the very threads of the universe's story. When scientists speak of a looking into deep space, they don't just mean distance, they mean history. Light doesn't travel instantly. It takes time, crossing the void year by year, century by century, until at last it brushes against a mirror or a lens. That means every time you look at the stars, you're also looking back. When you gaze at the moon, you see it as it was a little over a second ago. When you look at the sun, you're seeing light that began its journey about 8 minutes earlier. But James Webb takes this principle to an extreme. It can gather light that has been travelling not just for years or centuries, but for billions of years. So long, in fact, that the galaxies it reveals are caught in their infancy. It's easy to say that, but harder to really feel it. Imagine a camera so powerful that it could take a photograph of the Earth, and instead of showing you today's oceans and mountains, it showed you the first single-celled organisms stirring in the primordial sea. Webb isn't looking at Earth's past, but it is doing exactly that for the universe. And the most unsettling part is that what it has already shown us doesn't neatly fit the story we thought we knew. Before we step too far into what Webb has found, let me pause to ask you something personal. Where are you tonight as you listen to this? Maybe you're curled under blankets in a bedroom. Maybe you're lying on a couch with the lights low, or maybe you've put this on while travelling somewhere under a darkened sky. Whatever the case, the light from your lamp or the glow from your phone is bouncing around you in real time, but above, far past the ceiling, past the air, past the atmosphere, ancient light is still on its way. It is older than Earth itself, older than the Sun, older even than the galaxies you're familiar with. And now, thanks to James Webb, humanity can finally gather some of that ancient light and ask it questions. That's the heart of our story tonight. A telescope so sensitive, it can look to a time before the first galaxies were supposed to exist. A telescope that has already uncovered galaxies forming sooner, faster, and stranger than the standard model of cosmology ever predicted. A telescope that has made scientists wonder if our cherished timeline of the Big Bang is more flexible, more puzzling, maybe even more fragile than we once thought. Before I tell you about those discoveries, if you find this kind of journey calming, or if you feel a spark of curiosity as the night unfolds, I'd be so grateful if you left a like on this video, or perhaps subscribed. It helps bring more people into this little corner of calm exploration. And maybe it offers someone else the same restful curiosity you're feeling now. The James Webb Telescope is like no other instrument we've ever placed into the sky. It floats 1 million miles from Earth, far beyond the moon, tucked into a stable pocket of gravity called the second Lagrange point. There it unfolds its golden mirrors, each one polished to extraordinary precision. They reflect and focus light onto instruments that aren't tuned to visible wavelengths like your eyes, but to infrared. This allows Webb to see not just what is bright in starlight, but what is hidden behind veils of dust, what is stretched out by the expansion of the cosmos, and what lies beyond the reach of ordinary telescopes. And here is where the wonder begins. Because when Webb looks far enough, it is looking to a time before stars should have had the chance to form. Yet the images it has given us show something else entirely. Galaxies shining when they should not have existed yet. Massive clusters burning brightly in an era of supposed darkness. Black holes at scales that shouldn't have been possible so soon. The very architecture of the universe seems to appear earlier than the theories predicted. It is as if Webb has peeked behind a curtain we didn't know was there, and the scene is different from the script we had rehearsed for decades. This isn't to say that the Big Bang itself is disproven, though you may have seen such bold headlines. What it does mean is that the neat, tidy version of events we were once comfortable teaching, that galaxies took hundreds of millions of years to assemble, that the first stars required long stretches of cosmic time to ignite, no longer holds so firmly. Webb has shown us that the universe was busier, faster, and perhaps more inventive than we imagined, and all of this is wrapped in a gentle paradox, because as unsettling as these findings are, they also remind us how much more there is to learn. Science is not the story of answers nailed into place, but of questions unfolding. If Webb has taught us anything already, it is that the cosmos is far more restless than our textbooks, and perhaps even more surprising than our imaginations. When people hear about the James Webb Space Telescope, they often think of it as the successor to Hubble, a newer, shinier machine meant to take prettier pictures of the cosmos, and in one sense that's true. Hubble defined a generation of astronomy. It showed us the age of the universe, captured the deep fields where thousands of galaxies crowded into a single image, and revealed planets circling distant stars. To say that Webb is merely Hubble's replacement, though, is to miss how revolutionary it truly is. Because this isn't just an upgrade in resolution or in orbit. This is a shift in how we see the universe itself. Think about the human eye for a moment. You and I see in a narrow slice of the electromagnetic spectrum called visible light. Everything from red to violet, all the colours of the rainbow exist in that small band. But outside of it, the universe goes on. There are radio waves, microwaves, ultraviolet, X-rays, gamma rays, and most importantly for our story tonight, infrared. Infrared light is what you feel as warmth from a fire or from the sun on your skin. It's invisible to your eye, but not to instruments designed to capture it. And that's what makes James Webb so special. It isn't just a better telescope, it's a different kind of vision entirely. For decades, astronomers knew that to really peer into the early universe, you had to leave the realm of visible light behind. The reason is cosmic expansion. Ever since the Big Bang, space itself has been stretching. Light, as it travels across billions of years, is stretched too, its wavelength elongated. What begins as ultraviolet or visible light from the first galaxies is pulled further and further toward the red end of the spectrum. By the time it reaches us, it isn't visible light anymore. It has become infrared. To catch that light, you need an eye tuned to those long wavelengths. Hubble could see a little into that territory, but not far enough. Webb was designed entirely with this in mind. Picture its golden mirror, made up of 18 hexagonal segments. Together they span 6.5 meters across, more than twice Hubble's size. A bigger mirror means more light, and more light means fainter, more distant objects can be detected. But the mirror alone isn't enough. Infrared light is delicate, easily drowned out by heat. Even the faint warmth of the telescope itself would blind it to the ancient signals it's trying to catch. So Webb was built to stay cold, unbelievably cold. Its instruments operate at temperatures close to absolute zero, protected by a tennis court-sized sunshield that blocks the heat from the sun, earth, and moon. 5 layers of this shield, thinner than a human hair, keep one side scorching hot while the other side chills into darkness. Without that shield, the telescope simply couldn't see. The place where Webb sits is equally important. Hubble circles Earth every 90 minutes, always dipping in and out of sunlight and shadow, always feeling the glow of our planet beneath it. Webb, on the other hand, sits far away, about 1 million miles distant, at a gravitational balance point known as L2. Out there, it can keep its sunshield facing the sun while its mirrors stare forever into darkness. It doesn't orbit Earth. It orbits the sun, trailing behind us like a quiet companion. That stability is what allows it to maintain the freezing temperatures necessary for infrared astronomy. Now consider the instruments mounted behind the mirror. There's NIRCam, the near-infrared camera, capable of detecting the faintest galaxies. There's near-spec, the spectrograph, which can split that ancient light into its components and reveal what elements make up those first stars. There's MIRI, the mid-infrared instrument, which pushes Webb's vision even further into wavelengths that show dust, molecules, and planetary atmospheres. And there's FGS NIRIS, a fine guidance system that not only keeps the telescope locked onto its targets, but also contributes its own set of scientific capabilities. Together, these instruments form something like a symphony of sight, each one attuned to a different note of the infrared spectrum. This matters because the universe hides behind dust. Visible light is easily blocked. A cloud of interstellar gas can obscure a star completely. Infrared, though, slips through. It threads the veil, revealing what lies inside stellar nurseries where planets are born, or inside distant galaxies where star formation rages. For the first time, we can look not only at the edges of the observable universe, but also into the places that were once opaque. That's one reason James Webb is more than a telescope. It's a time machine and an X-ray of the cosmos rolled into one. It allows astronomers to watch galaxies forming when the universe was just a few 100 million years old. It allows them to see stars igniting in regions where Hubble saw only shadows, and it allows them to study exoplanets, worlds orbiting other stars, by capturing the faint fingerprints of molecules in their atmospheres. Already Webb has detected water vapour, carbon dioxide, methane and more in the skies of planets dozens of light years away. Not images of the planets themselves, not yet, but the first hints of their chemistry, which is arguably even more profound. But beyond the instruments, beyond the orbit, beyond the physics of infrared, there is the sheer ambition that makes Webb stand apart. It is the most complex space observatory ever built. Its mirror had to fold up to fit inside the rocket, then unfurl like a piece of origami in space. Its sun shield had to stretch out flawlessly, tensioned by motors that had never been tested in zero gravity before. More than 300 single-point failures existed in the design, meaning if just one of those components malfunctioned, the telescope would have been useless. No astronaut can fly out 1 million miles to repair it. If something had gone wrong, Webb would have been lost forever. The launch, the deployment, the alignment, all of it had to work perfectly, and it did. Against all odds, everything clicked into place, and the telescope began its mission. That fragility, that improbability, adds to its significance. For decades, Webb was delayed. Its cost ballooned. Its critics doubted it would ever fly. And yet, it is there now, watching the earliest galaxies, showing us images of the universe we never dreamed we'd see. The very fact of its existence is extraordinary. When the first images were released in July of 2022, people around the world saw galaxies whose light began billions of years ago, revealed in sharp detail, glowing in colours rendered from the infrared. Tiny arcs of lensed galaxies bent by gravity. Vast fields of stars glittering in young clusters. Nebulae swirling in complex filaments of dust and gas. Each picture was more than beautiful. It was evidence that Webb worked, that the decades of waiting had been worth it, and that the universe still had surprises to give. And then, as astronomers began to dig deeper, to analyse spectra, to push the limits of what the telescope could see, they found things they weren't expecting. Galaxies that seemed too massive, too mature, too early. Black holes growing too quickly. Structures forming faster than our models of cosmology predicted. These were not just pretty pictures, they were puzzles. Webb was showing us a universe that didn't behave exactly as our theories said it should. And that is why it matters more than any telescope before it. Because it is not just filling in details, it is challenging the foundation. In science, progress doesn't come only from confirmation, it comes from contradiction. When a new instrument reveals something that doesn't fit, it forces us to rethink. The Copernican revolution didn't happen because telescopes confirmed old ideas. It happened because telescopes showed moons orbiting Jupiter, phases of Venus, mountains on the moon. Evidence that demanded a new model. Webb's early discoveries may be the start of a similar shift. They may force cosmologists to adjust their understanding of how galaxies form, how stars ignite, how black holes grow, even how the Big Bang itself unfolded. And yet, even as it provokes these questions, Webb provides a comfort. It shows us that the universe is not static, not finished, not fully known. Every time we think we have reached the limit, there is another horizon. That is what makes James Webb more than just a telescope. It is a reminder that our curiosity can still outpace our certainty, that the sky is still larger than our imagination, and that even after centuries of astronomy, the universe still holds secrets waiting in the infrared glow of ancient light. When people talk about distance, they usually mean something simple, something measured in meters or miles, in steps across a room or hours spent behind the wheel. But when astronomers speak of distance, they almost always mean time. A galaxy is not just far away, it is also long ago. And the farther out you look, the older the picture becomes. This is because light, for all its speed, is not instantaneous. Even at 300,000 kilometers per second, the journey across space takes time. That delay turns the entire universe into a kind of museum of history, with every object frozen at the moment its light began to travel toward us. The moon is the nearest example, its reflected sunlight reaching us just over a second after it leaves. The sun is further, about 8 minutes in the past whenever we look up at it. The nearest star, Proxima Centauri, is more than 4 years away, which means its light began its journey while you were still living through a different season, a different year, perhaps even a different chapter of your own life. And beyond that, the scale grows quickly. The Andromeda Galaxy is visible to the naked eye, but the light that enters your eyes left that galaxy more than 2 million years ago. The picture you see is older than the entire history of human civilization. This layering of time is what makes astronomy so unusual. You can't ever see the universe as it is now. You can only ever see it as it was. Every glance is a glimpse into history stitched together across countless distances. Nearer galaxies show us adolescence. Mid-distance galaxies show us youth. The faintest smudges show us infancy. And if you can look deep enough, you might even glimpse something approaching the birth itself. That is the promise of telescopes like James Webb. When the first deep-field images came back, astronomers were struck not only by their beauty, but by their density. In a patch of sky, no larger than a grain of sand held at arm's length, Webb revealed thousands of galaxies. Each one contained billions of stars, many of which had planets, and all of them were at different points in the past. Some were relatively recent, a few billion years old. Others were almost unimaginably young, their light stretching back more than 13 billion years. That's a number so large that it loses meaning. To make sense of it, you have to think about the scale of your own life. A century is the longest a human might hope to live. 10 centuries make 1,000 years. 10,000 centuries take you back to the earlier cities, the first writing scratched into clay. And yet that span, impressive as it feels, is almost nothing compared to the billions of years these galaxies have been shining. And here is where things become stranger still. Because the farther you look, the more the very fabric of space alters the light itself. The expansion of the universe means that distant galaxies are not only far away in space, but also moving away in time. Their light is stretched, redshifted, pushed into longer wavelengths as space itself grows. What began as blue or ultraviolet light in those first stars is now deep infrared. To see it, you must have an instrument tuned to those colours. That is why Webb is built the way it is. Hubble could see part way, but not all the way. Webb reaches further, past that curtain, into the wavelengths that hold the first images of creation. Astronomers sometimes describe the universe as having a horizon, the cosmic microwave background. That faint glow, discovered in the 1960s, is the afterglow of the Big Bang itself, light released when the universe was just 380,000 years old. Before that, the universe was opaque. a hot fog of particles that scattered light like smoke. Only when atoms formed and the fog cleared could photons stream freely. The microwave background is the limit of what we can see in light. It is the edge of the visible universe. And yet in a way, Webb looks even further. Not in the sense of seeing before the background, but in the sense of piercing closer to that edge than any telescope has done before. Think of it like standing at the bottom of a canyon with mist ahead of you. Hubble allowed us to walk toward the mist and glimpse shapes emerging in the fog. Webb lets us step closer still, seeing details that were once blurred, finding structures we didn't expect to see so near the beginning. Galaxies, it turns out, had already formed in significant numbers. Their light now stretched to us across billions of years. This is what scientists mean when they talk about looking back in time. It isn't a metaphor, it's literal. The light from those galaxies left when the universe was just a few 100 million years old. It has been travelling ever since, finally arriving now, just as humanity builds a telescope capable of receiving it. That coincidence is humbling. Out of billions of years, we exist in the brief window when such light can be seen, and when a species has the technology to interpret it. In another few billion years, cosmic expansion will have carried those galaxies beyond our horizon. Their light will never reach us again. We are lucky to exist now, at a time when the universe is still readable, still revealing its history. To picture this better, imagine a photo album where the pages are scattered across the room. You can only collect them if you're standing at the right place, at the right time. That is what the night sky is. A scattered album, fragments of history arriving all at once. Some pages are fresh, some are faded, some are so old they are barely legible, and yet together they tell the story of everything that has ever existed. Webb is the tool that lets us read the oldest, faintest pages, and what those pages show is unsettling. Because instead of faint smudges struggling to become galaxies, Webb shows us surprisingly complex structures. Galaxies with disks, galaxies with bulges, galaxies that look too mature for their age. It is like opening a baby photo and finding an adult face staring back at you. Something about our timeline of growth is missing. The curtain of light doesn't reveal a gradual unfolding, but a sudden appearance of things we thought would take much longer to form. This discovery matters not only for cosmology, but for the way we think about beginnings. We often imagine the universe unfolding step by step in neat chronological order. First the Big Bang, then atoms, then stars, then galaxies, then planets, then life. But Webb shows us that the order is less tidy. Galaxies may have leapt into existence faster, stars may have ignited sooner, black holes may have grown at breakneck speed. The curtain of history is not a slow rise but a more tangled performance, one we're only beginning to piece together. And yet, as strange as this is, it also fits a pattern we've seen before. Every time we build a better instrument, the universe becomes more complicated. The first telescopes showed moons around Jupiter and rings around Saturn, things that didn't fit the ancient idea of perfect celestial spheres. Later telescopes showed galaxies beyond our own, challenging the idea that the Milky Way was the entire cosmos. Hubble showed us a universe filled with far more galaxies than we had guessed. And now Webb shows us that even at the very beginning, the universe was already more advanced than we imagined. Each step deeper adds complexity, not simplicity. This is why astronomers talk about a cosmic curtain. It is not just distance, it is a veil of time, drawn across billions of years. Pull it back, and you don't just see more stars, you see a younger cosmos, stranger, and more raw, but also surprisingly familiar. Structures appear where none should exist. Order emerges faster than chaos would suggest, and the laws of physics, the ones we thought we understood, seem to hint at secrets still waiting behind the glow of infrared light. If Webb can look so far back, what does it truly mean to peer past the Big Bang? How can a telescope bound by light glimpse something from a time when light itself was barely free to move? When people hear the phrase looking past the Big Bang, it sounds almost impossible, like saying you've peeked behind the beginning of everything. The Big Bang is usually described as the ultimate starting point, the moment when space, time, energy, and matter all came into existence. How could anything exist before that? And how could a telescope, even one as powerful as James Webb, see it? The truth is a little subtler and a lot more fascinating. To understand it, we need to think carefully about what we mean when we talk about beginnings, about light, and about the difference between theory and observation. The Big Bang, as cosmologists use the term, isn't a single flash in the dark like a firework. It's the name we give to the rapid expansion of the universe from an unimaginably hot, dense state. It doesn't describe the exact instant of creation itself, but the earliest phase of growth that our physics can currently model. If you roll the cosmic movie backward, galaxies come closer together, stars vanish, atoms break apart, particles collide, and eventually you reach a point where the equations fail. Beyond that point, we don't really know what happened. The Big Bang is our shorthand for the edge of knowledge. Now, here's the complication. Light couldn't travel freely in the very earliest times. For the first few 100,000 years, the universe was so dense with particles that photons bounced around endlessly, never making it far before scattering. It was an opaque fog. Only when the universe cooled enough for atoms to form did the fog clear, and light began streaming outward. That release of light is what we now see as the cosmic microwave background. It's the farthest we can look with photons, the wall of the visible universe. So when someone says Webb is looking past the Big Bang, they don't mean it literally sees before time began. What they mean is that Webb is pushing closer and closer to that wall, capturing the very first galaxies and stars to appear once the fog cleared. It's like standing in a forest after a thick mist lifts. You can't see the moment the mist was everywhere, but you can see the first shapes that emerge when it begins to thin. Webb's infrared vision is tuned to those shapes, the faint galaxies just after the beginning of transparency. And yet, even with that clarification, Webb has revealed things that feel like glimpses beyond what was supposed to be possible. Because according to our best models, galaxies shouldn't have been so large or so structured so soon after the fog lifted. The early universe should have been a place of small, chaotic clumps slowly merging. Instead, Webb shows us galaxies shining with billions of stars, some less than a few 100 million years after the Big Bang. That's like walking into a nursery and finding not newborns, but teenagers already standing tall. It raises the question of whether our timeline is wrong, or whether something before the fog seeded structure in ways we don't yet understand. This is where theories begin to stretch. Some cosmologists wonder if the expansion in those first moments was faster or stranger than we think. Others ask whether the laws of physics we use today fully applied back then. There are even suggestions that what we call the Big Bang might not have been the absolute beginning, but one phase of a larger cycle. Perhaps the universe expands and contracts endlessly, and we are living after the most recent bounce. If that were true, then what we call before the Big Bang wasn't nothing, but another universe in a different configuration. Webb doesn't directly prove that, but its discoveries breathe life into these possibilities by showing us objects that shouldn't exist so soon otherwise. Another angle comes from inflation theory, the idea that just after the Big Bang the universe expanded faster than the speed of light for a tiny fraction of a second. This solves many puzzles, like why the universe is so uniform on large scales, but if inflation happened, it may have also left imprints. Ripples of density, seeds for galaxies, traces that we're only now beginning to detect. Webb can't see the inflationary moment itself, but it might be catching the consequences. Galaxies forming earlier than expected because the seeds planted were richer than our models assumed. And then there is the possibility that dark matter, the invisible substance making up most of the universe's mass, played a more active role in the beginning than we realized. If dark matter clumped quickly, it could have pulled normal matter along with it, triggering galaxies earlier. Webb's findings of mature galaxies so soon after the Big Bang could be evidence of this unseen scaffolding. Once again, Webb doesn't see the Big Bang directly, but it shows us the structures that hint at what was happening before light could escape. So when people say Webb looked past the Big Bang, what they are really capturing is the sense that our boundary for the beginning is shifting. What we thought would be empty or chaotic turns out to be full of unexpected order. The fog lifted, and instead of nothing much, there were already galaxies waiting. That forces us to ask, what prepared the universe for such a quick start? Did something happen in those first fractions of a second, or even before, that set the stage? The telescope is like a historian reading the earliest chapter of a book and realizing it begins mid-sentence, implying there was another page before it. This idea of before is slippery though. If time itself began with the Big Bang, then asking what came earlier might be meaningless. But physics doesn't let go so easily. Equations can be extended, alternative models can be tested, and evidence can be searched for. Webb's job is to supply the evidence, to show us whether galaxies formed earlier than our equations allow, whether stars lit up faster than nuclear physics predicts, whether black holes appeared in ways we can't yet explain. And so far, the evidence is pointing toward surprises. For you, listening tonight, it might feel almost impossible to imagine. Billions of years compressed into metaphors, models, and numbers, but think of it like standing at the shore of a vast ocean. You can't see the very bottom, but you can see the waves at the surface. By studying those waves, you can infer what lies beneath. Webb is showing us the waves at the cosmic shore, and they don't quite match the patterns we expected. That is why astronomers speak with such excitement, even shock, about what the telescope has found. And all of this carries a quiet reminder. Our story of the universe is not final. It is still being written. Every time we think we've traced it back to the very start, new evidence suggests there may be more. Webb doesn't literally see past the Big Bang, but it does pull us closer to that mysterious edge, closer than any human eyes have ever come. And in doing so, it invites us to rethink what beginning really means. When the James Webb Space Telescope sent back its earliest images of the deep universe, astronomers expected faint smudges, small beginnings, the first awkward steps of galaxies just starting to come together. What they actually found was something else entirely. In the dark, young universe, less than a few 100 million years after the Big Bang, Webb revealed bright, well-formed galaxies, some already massive, some already structured in ways no one predicted. The discovery was so startling that more than a few scientists described it as shocking, not because they didn't think galaxies could exist then, but because they shouldn't have existed in the form Webb was showing them. They were younger than the timeline allowed, but older in appearance than they had any right to be. To appreciate why this matters, you have to step back and consider the timescale. After the Big Bang, the universe began hot and dense. For hundreds of thousands of years, it was an opaque fog of particles. When it cooled, atoms formed and a light could travel freely, giving us the cosmic microwave background. But that wasn't the moment galaxies appeared. For a long while after, the universe was dark, filled with neutral hydrogen gas, with no stars to light it. Astronomers call this period the cosmic dark ages. Only when gravity pulled matter together into the first stars did the darkness lift. Those stars in turn formed the earliest galaxies. The expectation was that this took time, hundreds of millions of years at least, before galaxies reached any significant size. Webb's findings challenged that neat picture. In data from its first surveys, astronomers identified galaxies existing when the universe was only about 300 to 400 million years old. That's just a blink compared to the 13.8 billion years of cosmic history. And yet these galaxies weren't tiny seeds. They were big. Some contained as many stars as the modern Milky Way, though compressed into smaller spaces. They had mass, they had structure, and in some cases they appeared to already have star populations that looked old. This shouldn't have been possible. Why is it so puzzling? Think of galaxy formation like building a city. First you gather bricks, then you assemble small houses, then neighbourhoods, and eventually a sprawling metropolis emerges. But Webb is showing us that some of these cosmic cities were already bustling with skyscrapers while, according to our models, the bricks should barely have been laid. The laws of physics haven't changed, so something about our understanding of the timeline must be incomplete. Either galaxies formed faster than we realised, or the conditions of the early universe gave them a head start. Astronomers began to check and recheck the data. Were these really galaxies? Could Webb have mistaken something else for them? The light Webb sees is stretched red-shifted by the expansion of the universe. Measuring that redshift tells you how far away and how far back in time the galaxy is. For the earliest candidates, the redshift values were extraordinary. At first, some researchers wondered if they were errors, if the galaxies were closer and simply disguised as distant ones by dust or by odd emission lines. But as more detailed spectra came in, the results held. These really were galaxies from the first few 100 million years, and they really were large. This raises several possibilities. One is that star formation in the early universe was far more efficient than our models suggest. Perhaps gas collapsed quickly, igniting stars in rapid bursts, and entire galaxies grew almost overnight in cosmic terms. Another is that dark matter, the invisible framework of the universe, clumped earlier and more densely, pulling normal matter into galaxies at a faster pace. Some theories even suggest that the physics of the early universe could have been slightly different, allowing matter to cool and collapse more easily than it does today. Whatever the reason, the discovery forces us to rethink. Our picture of galaxy evolution was built largely on data from Hubble and ground-based telescopes, which could only peer so far. They suggested a gradual build-up, with galaxies small and irregular in the first billion years, merging over time into larger structures. Webb, with its infrared eyes, is pushing deeper and showing us that the process may have been jump-started. Instead of stumbling beginnings, we see a headlong rush into complexity. For astronomers, this is both thrilling and unsettling. On one hand, it means the universe is even more dynamic than we imagined, filled with surprises waiting to be discovered. On the other, it means that many of the comfortable models, the neat timeline as written in textbooks, need to be revised. This isn't unusual in science, it's how progress happens. But the scale of the revision is what has people talking. If galaxies could be so massive so soon, then maybe our understanding of the earliest moments, the conditions just after the Big Bang, is incomplete. Think for a moment about what these galaxies represent. Each one contains billions of stars. Those stars are forging heavy elements, creating the building blocks of planets, of chemistry, of life itself. The earlier galaxies appear, the earlier those elements are seeded into the universe. That could mean the potential for planets and life emerge sooner than anyone thought. It shifts not only our picture of cosmology, but also our place in the story. If galaxies and stars formed quickly, then perhaps the universe was ready for complexity much earlier than we believed. There's also the question of black holes. Webb has revealed candidates for massive black holes existing shockingly early. Normally, black holes grow from collapsed stars, slowly feeding on gas and merging with others. To reach the sizes Webb suggests in just a few 100 million years, they must have grown at extraordinary rates, or perhaps formed directly from collapsing clouds without first passing through a stellar stage. This ties directly into the mystery of the galaxies. Massive black holes and massive galaxies seem to appear hand in hand, each influencing the other, each demanding explanations that stretch current theory. One of the most striking images from Webb's early data is the so-called cosmic cliffs in the Carina Nebula. While that image shows a star-forming region in our own galaxy, it illustrates the power of infrared to cut through dust and reveal hidden structures. Apply that same power to the deep universe, and suddenly galaxies that were invisible to Hubble stand out in sharp relief. Webb has pulled back a veil, and what lies behind it isn't emptiness but a bustling crowd of galaxies, far more mature than expected. For those listening tonight, it might feel abstract, this idea of galaxies billions of light years away. But consider it like this. Imagine looking at an old family album. You expect to see pictures of a baby in the earliest pages. Instead, you find photographs of a grown adult where only infants should be. That is the puzzle astronomers face. The early universe, in theory, should show baby galaxies. Webb has shown us galaxies that look like adults wearing newborn dates. Some skeptics still urge caution. The field is new and the data is complex. Spectra need to be confirmed, interpretations debated. Science is careful for a reason. But the weight of evidence is growing, and with it the sense that the first galaxies were younger than the universe's age would suggest, yet older in form than models predict. It is as if time itself moved differently for them, or as if the universe had a way of rushing through its infancy. What does this mean for us now? It means that every new Webb survey is eagerly awaited. Each deep field may reveal more of these anomalous galaxies, adding to the tension between theory and observation. It means that cosmologists are already drafting new models, tweaking parameters, exploring ideas that once seemed too exotic. And it means that once again, we're reminded how provisional our knowledge is. The first galaxies are not just points of light. They are signposts, telling us where our theories fail, guiding us toward a deeper understanding. And as Webb continues its mission, the surprises are likely to grow. We are standing at the threshold of a new era in astronomy, one where the neat timelines of the past are giving way to something more complex, more challenging, and more exciting. When astronomers first turned the James Webb Space Telescope toward the earliest galaxies, one of the biggest surprises wasn't just the galaxies themselves, but what filled them. Inside those young systems, so soon after the Big Bang, there appeared to be stars already well developed. Stars that should have taken far longer to form. It's as though the universe, still fresh from its earliest moments, had skipped several steps and leapt straight into maturity. To understand why this is such a puzzle, it helps to think about how stars normally form. In the simplest sense, a star is the result of gravity pulling gas together until it becomes dense enough and hot enough for nuclear fusion to ignite. Hydrogen atoms fuse into helium, releasing energy, and the star begins to shine. But this process takes time. Clouds of hydrogen and helium first need to cool, to clump, to collapse, to overcome turbulence and pressure. Even in the modern universe, where conditions are calmer and well understood, star formation is not instant. For the first stars, known as Population 3 stars, it should have been even slower. Population 3 stars are the theoretical first generation, formed entirely out of primordial hydrogen and helium, with no heavier elements. They were expected to be massive, short-lived, and rare to observe directly, but crucial for shaping the early cosmos. Their nuclear furnaces would have created the first heavier elements: carbon, oxygen, iron, the building blocks of later stars, planets, and life. Without these early stars, galaxies couldn't have evolved into what we see today. But according to theory, those stars should have taken time to form after the cosmic dark ages. Hundreds of millions of years should have passed before enough of them gathered to make galaxies shine brightly. Webb, however, is suggesting otherwise. In some of the earliest galaxies it has observed, there are indications of stars with heavy elements already present. That means not only had Population 3 stars formed, but they had also lived, died, and spread their enriched material into space, allowing later generations, Population 2 stars, to appear. And all of this seems to have happened far faster than the models allowed. Stars weren't supposed to be so fully developed, so chemically evolved, so soon after the Big Bang. The data come from spectra, the fingerprints of light. When Webb captures light from these early galaxies and splits it into its component wavelengths, it reveals what elements are present. The surprising part is that some of these young galaxies show evidence of metals. Astronomers use metals to mean any element heavier than helium. The presence of those metals means at least one earlier generation of stars had already lived and died, which is extraordinary, because by the timeline we expected, there shouldn't have been enough time for even one generation to go through its full life cycle. This discovery raises several questions. Did the first stars form faster than we realized? Were they even larger and shorter lived than theory predicted, racing through their lifespans in just a few million years and enriching their surroundings almost immediately? Or is there something missing in our understanding of how matter cooled and clumped in the young universe? One possibility is that the density of gas in the early universe allowed for quicker star formation. With more raw material packed closely together, gravity could have pulled stars into being more rapidly. Another is that turbulence and feedback, processes that slow star formation today, were less effective back then, letting the first clouds collapse almost unchecked. Yet another idea is that dark matter, the invisible glue of the cosmos, provided deeper wells of gravity, pulling stars into existence faster than expected. Each explanation has some merit, but none fully resolves the puzzle. There is also the question of what these first stars looked like. Were they truly as massive as some models suggest, hundreds of times the mass of the Sun, blazing so brightly and briefly that they barely lasted before exploding as supernovae? If so, their debris would have spread metals quickly, but their fleeting lives would have been hard to capture directly. Webb may never see those first stars individually, they may be gone too quickly, but it may see their fingerprints in the galaxies they helped shape. And then there is the matter of black holes. If some of those early stars collapsed directly into black holes, they could have seeded the massive black holes Webb is now finding at the centres of young galaxies. That would help explain how such huge black holes appeared so soon. It ties the puzzle of stars and the puzzle of galaxies together, suggesting they may not be separate mysteries but two sides of the same early process. For astronomers, this is both exhilarating and daunting. The neat sequence of events, dark ages, first stars, first galaxies, enrichment, then more stars, no longer looks so neat. Instead, it seems the universe rushed through these steps, collapsing them into a much shorter timescale. The stars Webb has revealed look fully formed in an era when theory said they should barely exist. What does this mean for us? On a human scale, it highlights just how quickly complexity can emerge. The universe didn't linger in simplicity. Within a tiny fraction of its lifespan, it had already moved from uniform gas to blazing stars to enriched galaxies filled with elements that would one day make life possible. That speed challenges our expectations, but it also reminds us that creation can be more efficient, more inventive than we predict. There's also a deeper implication. If stars formed so quickly, then the universe was capable of building planets sooner than expected too. Planets need heavier elements, forged in the cores of stars. If those elements were present early, then rocky planets could have begun forming not billions of years later, but perhaps within the universe's first billion years. That raises profound questions about the timeline for life. Could life have begun somewhere long before Earth was even formed? If the building blocks were there, the possibility can't be dismissed. Still, the mystery remains. How could so much happen so quickly? Some scientists now propose that our cosmological models need revision. Perhaps the expansion rate of the universe in its earliest moments was slightly different than we assume. Perhaps star formation in the primordial gas followed rules we don't yet understand. Or perhaps there is something entirely new, some missing ingredient in our physics waiting to be uncovered. Webb doesn't answer these questions yet, but it forces us to ask them, and the puzzle is far from over. The deeper Webb looks, the more of these unexpectedly mature stars and galaxies it finds. Each one adds weight to the case that our timeline needs adjusting. Each one is a reminder that the universe is stranger than our equations alone can capture. For you listening tonight, think of it like walking into a theatre just as the curtain rises. You expect to see the actors step onto the stage one by one, slowly introducing the story. Instead, the stage is already crowded, the actors already mid-dialogue, the plot already advanced. That is what Webb has revealed about the earliest stars. The performance had already begun, and we're left to wonder what opening act we missed. And as we move further into this journey, the next question is even more daunting. Because if stars and galaxies were already mature so soon, then what about the black holes that anchor them? How could something so dense, so massive, appear so early in cosmic history? Among all the surprises the James Webb Space Telescope has brought back, perhaps the most unsettling are the black holes. These are not ordinary black holes, the remnants of dead stars scattered through the galaxies we know. These are giants, supermassive black holes, already weighing millions or even billions of times more than the Sun, and appearing in a time when the universe itself was still in its infancy. Their presence so early is one of the sharpest puzzles Webb has thrown at cosmology. To appreciate the mystery, it helps to remember how black holes normally form. In today's universe, a massive star can end its life by collapsing under its own gravity, leaving behind a black hole a few times the mass of the Sun. Over time, that black hole can grow by merging with others, or by pulling in gas from its surroundings. Given enough billions of years, such feeding can produce the titanic black holes we see at the centres of galaxies like the Milky Way. Ours weighs about 4 million solar masses, and it has had more than 13 billion years to reach that size. But Webb is showing us black holes in galaxies that existed less than 1 billion years after the Big Bang, some of them already weighing hundreds of millions of solar masses. By the usual rules, there simply hasn't been enough time for them to grow that large. It would be like finding a towering tree in a forest only a few months after planting the seeds. Something about the timeline doesn't add up. Astronomers have a few theories about how this could be possible. One is that the very first stars were so massive that when they collapsed, they left behind unusually large black hole seeds, perhaps hundreds of times the mass of the Sun instead of just a few. These heavier seeds could then grow faster, reaching supermassive status more quickly. Another idea is that some regions of the early universe allowed for direct collapse, where enormous clouds of gas fell inward under gravity without forming stars first, creating black holes of tens of thousands of solar masses right away. With such a head start, these black holes could have grown into giants within the short window Webb is observing. There's also the possibility that accretion, the feeding process by which black holes grow, was far more efficient in the early universe. Today, gas falling into a black hole often heats up and pushes back, limiting how fast the black hole can grow. But if conditions back then allowed for steady, rapid feeding without much pushback, growth rates could have been dramatically higher. Some models even suggest super-Eddington accretion, a regime where black holes devour material faster than the theoretical limit set by today's physics. Webb's data are still being parsed, but already the evidence points to black holes that were not only present early, but also influencing their galaxies. In some of the earliest galaxies Webb has examined, the light curves and spectra show the signatures of active galactic nuclei, black holes at the centres blazing as they feed, releasing more energy than the surrounding stars combined. That means these black holes weren't quiet passengers. They were shaping the development of their host galaxies, regulating star formation, and driving winds of gas outward. This deepens the puzzle because it ties two mysteries together. The early galaxies appear more mature than expected, and at the same time their central black holes appear larger than expected. Perhaps the two are linked. Black holes and galaxies seem to grow together, a relationship astronomers have seen in the modern universe as well. The mass of a galaxy's central black hole correlates with the mass of its stars, as though the two co-evolve. If that relationship holds true even in the earliest times, then the fact that Webb finds both mature galaxies and massive black holes makes sense. The problem is that both matured too soon. It's as though nature hit the fast-forward button on the very first structures in the cosmos. For cosmologists, this is not just a minor adjustment. It raises fundamental questions about the physics of the early universe. Did gravity behave differently under those extreme conditions? Did dark matter halos create deeper wells of attraction than expected, pulling in gas faster? Or is there something about the way we measure distances and times at such high redshifts that introduces hidden biases. Each possibility is under study, but none yet resolves the tension completely. And the mystery doesn't stop at growth rates. There's also the question of how these black holes lit up so brightly so soon. Quasars, galaxies with hyperactive central black holes, have been seen at great distances before, even by Hubble and ground-based observatories. But Webb adds detail and depth, confirming not only that they existed, but that some were astonishingly luminous in the first few 100 million years. To shine that brightly, they must have been consuming matter at prodigious rates. That again suggests a universe more efficient at building complexity than our models predict. For those listening tonight, imagine this. You expect a quiet dawn, the first faint glow on the horizon. Instead, as the sun rises, the sky's already ablaze with fireworks. That's what these black holes represent. At a time when the universe should still have been quiet, they were already roaring, already shaping the galaxies around them, already marking their presence in light that has taken over 13 billion years to reach us. Some scientists have even proposed more radical explanations. Perhaps black holes can form not just from stars or collapsing gas, but from fluctuations in the very fabric of space-time during the earliest moments of the universe. These so-called primordial black holes would have been born almost instantly after the Big Bang, and some might have survived to seed the galaxies Webb now observes. If true, it would mean black holes are not just products of cosmic evolution, but participants from the very beginning. The idea remains speculative, but Webb's findings keep it alive. Because without such exotic mechanisms, the growth rates required for these early giants stretch the limits of conventional astrophysics. If primordial black holes exist, they could explain not only the anomalies Webb sees, but also some of the puzzles of dark matter. But confirming their existence would require far more evidence Webb may or may not be able to supply directly. Even without that extreme idea, the evidence already forces a reconsideration of black hole physics. The early universe was not a calm place, slowly building toward complexity. It was active, dynamic, and full of gravitational monsters long before anyone expected them. And those monsters were not hidden. They were blazing with energy, detectable even across the vast gulf of time. For astronomers, there's both humility and exhilaration in this. Humility because once again the universe refuses to match our expectations. Exhilaration because each mismatch is a chance to learn something new. The black holes at the dawn of creation are not failures of theory, but invitations to expand it. They remind us that our picture of the cosmos is still incomplete, still being painted in detail, and the presence of those early black holes has wider implications. If they grew so quickly, then their feedback on galaxies may have been stronger, shaping star formation earlier than thought. If they were seeded in unusual ways, then the entire history of structure formation may need reworking. And if they were truly primordial, present from the very first instance, then our concept of the Big Bang itself may need to be revised. Webb has only just begun its mission, and already it has upended our sense of timing. The next surveys will probe even deeper, looking for fainter galaxies, smaller black holes, more subtle clues. Each observation will refine the puzzle, narrowing the possibilities but perhaps also opening new mysteries. That's the rhythm of science, a rhythm Webb has accelerated dramatically. For now, what we know is this. Black holes were there at the dawn of creation. They were large, they were active, and they were shaping the universe sooner than we thought possible. Their existence challenges our models, stretches our imagination, and forces us to ask what we still don't know. If galaxies and black holes appeared so early, then what about the rest of cosmic structure? When the James Webb Space Telescope opened its golden mirrors and began its first surveys, astronomers expected to find the faintest hints of galaxies near the edge of the observable universe. Small clusters of stars, irregular and fragile, just beginning to assemble into the systems we recognize today. What Webb actually revealed were galaxies far too big, far too bright, and far too structured for their age. These weren't just galaxies earlier than expected. These were galaxies that shouldn't exist at all according to the standard models of cosmic evolution. The puzzle begins with what cosmologists thought they understood about the early universe. After the Big Bang, matter took time to cool and condense. Hydrogen and helium gas had to collapse under gravity into the first stars. Those stars had to gather into clumps, merging into larger collections. Over hundreds of millions of years, those clumps grew into galaxies. The whole process was thought to be gradual, a slow layering of structure across cosmic time. By the first billion years, there should have been small galaxies, yes, but not the kinds of large luminous ones Webb has already found. Instead, Webb's surveys have shown galaxies that are already massive within just a few 100 million years of the Big Bang. Some appear to contain as many stars as the Milky Way, though in more compact spaces. Others display organized disks or bulges, features that should have taken billions of years to assemble. When these results first appeared, many astronomers responded with disbelief. Surely there had to be a mistake. Perhaps the distances were miscalculated. Perhaps what looked like mature galaxies were actually closer objects masquerading as distant ones. But as more observations came in, the evidence grew harder to ignore. The galaxies are really there, and they are really that old. The implications are staggering. If galaxies could form this quickly, then our models of structure formation need serious revision. Either the processes that build galaxies are far more efficient in the early universe than we realized, or something fundamental is missing from our understanding. Some researchers have suggested that the initial density fluctuations in the young cosmos were larger than expected, giving galaxies a head start. Others propose that dark matter clumped earlier, providing deep gravitational wells that accelerated growth. But even with these adjustments, the sheer mass of some of these galaxies strains belief. To put the problem in perspective, consider how galaxies grow today. A large galaxy like the Milky Way contains hundreds of billions of stars and has taken over 13 billion years to reach its current form. It grew by accreting smaller galaxies, by merging, by drawing in gas and slowly converting it into stars. That slow accumulation is what theory predicts. Yet Webb is finding galaxies that seem to have done all of that in a tiny fraction of the time. They are cosmic overachievers, rushing through evolution at breakneck speed. And it's not just their size. Some of these galaxies appear surprisingly orderly. Disk-like shapes, spiral structures, and even hints of mature star populations show up in data from epochs when the universe was supposed to be chaotic and unsettled. How could order have emerged so soon? If the early universe was a turbulent place, with constant collisions and mergers, then galaxies should have looked irregular, lumpy, and unstable. Webb's images show that some didn't. They settled into recognizable structures astonishingly early. This challenges not only astrophysics, but also cosmology at its core. The standard model of the universe, known as lambda CDM, has been extraordinarily successful at explaining observations on large scales. It combines the cosmological constant, representing dark energy, with cold dark matter, which shapes structure. According to this model, galaxies form slowly, hierarchically, from the bottom up. Small clumps merge into larger ones, and only after billions of years do the massive systems we see today come into being. Webb's galaxies don't fit neatly into that picture. If lambda CDM is correct, then either we've misunderstood the details of how baryonic matter, the ordinary gas in stars, evolves inside dark matter halos, or else some new ingredient is required. It's possible that feedback processes like supernovae and black hole winds behaved differently in the early universe, allowing faster star formation. Or perhaps star formation in dense early environments was simply more efficient. But the possibility that something deeper is missing cannot be ruled out. For listeners tonight, imagine walking into a library where the shelves are supposed to be empty at the start. According to the plan, books are added one by one over many years. But when you step inside on the very first day, you find entire sections already filled, with volumes stacked and organised. That is what Webb has shown us. The cosmic shells weren't empty. They were already stocked with galaxies we didn't expect to find so soon. And this has ripple effects. If galaxies were large and luminous so early, then the reionization of the universe, the process by which the first stars and galaxies ionize the surrounding hydrogen gas, may have happened faster than expected too. Webb is already helping to measure this, showing that light from these early galaxies was powerful enough to transform the universe from neutral to ionized in a relatively short span of time. That transition was a key milestone in cosmic history, and its timing is now being rewritten. Some astronomers remain cautious, pointing out that Webb is still in its early days, and that more detailed spectra are needed to confirm the true nature of these galaxies. But the trend is clear. The more Webb looks, the more of these anomalously massive mature galaxies it finds. And with each discovery, the case grows stronger that the universe's earlier structures were far more developed than we ever thought possible. This raises questions not just about the past, but also about the future. If galaxies formed so quickly, what does that mean for the timescale of life? Stars in those galaxies would have forged heavy elements early, enriching their surroundings with the material needed for planets. Could rocky worlds have formed within the first billion years of cosmic history? Could conditions for life have existed while our own Milky Way was still just a cloud of gas? These are speculative questions, but Webb's discoveries make them worth asking. The shock of these galaxies lies not only in their existence, but in their abundance. They aren't rare outliers. Webb is finding them in numbers that suggest early maturity was common. That means the universe itself was more capable, more productive than the neat models assumed. It's not just a story of a few exceptions. It may be the new normal. And so we're left with a universe that feels both familiar and alien. Familiar because galaxies are still the basic building blocks, gathering stars, gas, and black holes. Alien because they appear at times and in forms that don't match the script we thought we had. Webb hasn't just shown us pretty pictures, it has thrown down a gauntlet to theory, daring us to revise our understanding. When cosmologists first built the modern timeline of the universe, they imagined it as a neat sequence of stages. The Big Bang happened, followed by a period of inflation, then the formation of the first atoms, the release of the cosmic microwave background, the Dark Ages, the ignition of the first stars, the birth of galaxies, the seeding of black holes, and eventually the universe we see today. Each stage was supposed to unfold in order, one after the other, with timescales carefully worked out by models and confirmed by observation. For decades, this timeline seemed to hold. It matched the microwave background. It explained the distribution of galaxies. It predicted how structures grew from small fluctuations into the large-scale web of clusters and voids. Then James Webb came along, and suddenly the sequence began to fray. The telescope revealed galaxies too large, stars too mature, and black holes too massive in epochs, when, by the established chronology, they should have been barely beginning to exist. What Webb has done is not just find anomalies here and there, but gather enough of them to raise a deeper question. Is the timeline itself? To understand why this matters, it helps to picture the universe as a kind of cosmic calendar. Each billion years after the Big Bang is a page. The models told us what should appear on each page. First stars around page 0.2 or 0.3, first small galaxies around page 0.4, bigger galaxies by page 1, black holes taking longer, full-scale cosmic structures only after several pages had turned. But Webb's data suggests that when you flip to the early pages, they are already crowded with entries that belong to later ones. Galaxies that shouldn't appear until page 2 or 3 are already written onto page 0.4. That misalignment suggests the calendar itself may be off. One possibility is that the rate of star formation was underestimated. Perhaps the conditions in the early universe were so favourable to forming stars and galaxies that they reach maturity much faster. That would compress the timeline, making events that were supposed to take hundreds of millions of years unfold in tens of millions instead. But if that were true, why did the models underestimate it so badly? Star formation is based on physics we think we understand. Gas cooling, collapsing, igniting. If we were wrong about how quickly it happens, it means some fundamental piece of the puzzle is missing. Another possibility is that dark matter played a larger role earlier than expected. Dark matter, though invisible, provides the scaffolding for galaxies to form. Its gravity pulls normal matter into halos where stars and galaxies can grow. If dark matter clumped sooner or more strongly than models predict, galaxies could have formed faster. That might explain some of Webb's anomalies. But the standard cosmological model already includes dark matter, and it was tuned to match observations like the cosmic microwave background. If we change how dark matter behaves, we risk breaking the model's success in other areas. There's also the suggestion that the timeline might not just be compressed, but fundamentally shifted. Some researchers have floated the idea that the age of the universe might be slightly older than the standard 13.8 billion years. If that were true, then galaxies appearing earlier than expected might not be so surprising. They would have had more time to form. But adjusting the age of the universe isn't trivial. The 13.8 figure comes from precise measurements of the microwave background, the expansion rate, and the distribution of galaxies. Changing it would mean reworking some of the most successful parts of cosmology. Still, the mere fact that it's being discussed shows how disruptive Webb's findings have been. And then there is the more radical possibility that our understanding of cosmic expansion itself is incomplete. If the early universe expanded differently than we think, perhaps faster, perhaps with varying rates, then the relationship between distance, time, and redshift might need to be revised. Redshift is the key to placing galaxies on the timeline. It tells us how much their light has been stretched by the expansion of space. If our interpretation of redshift is even slightly off, then our placement of galaxies on the cosmic calendar could be skewed. This is controversial, because redshift has been the bedrock of cosmology for nearly a century. But Webb's results have made some scientists at least entertain the thought. For those listening tonight, think of it like a clock you've trusted all your life. Every appointment, every schedule, every event has been planned by that clock, and it always seemed accurate. Then someone shows you photographs that don't fit the times it claims. People appear older than they should be. Events seem to have happened before they were possible. You can either assume the photos are wrong, or you can start to wonder if the clock itself isn't keeping perfect time after all. That's where cosmology finds itself with Webb's discoveries. It isn't the first time the timeline of the universe has been challenged. A century ago, before Hubble discovered the expansion of the universe, astronomers believed the cosmos was static and eternal. That model collapsed when galaxies were found to be racing away from us. Later, when the first measurements of cosmic expansion suggested the universe was younger than some of its oldest stars, cosmologists had to refine their calculations. Each time the timeline was adjusted to fit the evidence, Webb may be forcing another such adjustment. What makes this different is the sheer scale. We're not just talking about fine-tuning numbers, we're talking about entire stages of cosmic history appearing out of order. Black holes where there should be none. Galaxies fully formed when they should still be fragments. Stars with metals when they should still be pristine. It's not one discrepancy, it's a pattern. Some scientists suggest that what we're seeing is a sign of new physics. Perhaps there are forces or particles we don't yet know about that accelerated cosmic evolution. Perhaps gravity behaved differently under extreme conditions. Perhaps the interplay between dark matter and ordinary matter is more complex than assumed. These are speculative ideas, but Webb's data demands speculation. The standard timeline is no longer unquestioned. For ordinary listeners, it's easy to get lost in the details, but here's a way to think of it. Imagine writing a story about someone's life. You carefully outline the chapters: birth, childhood, adolescence, adulthood. Each stage has its expected order and timing. Then someone hands you a photograph of the person as a grown adult dated to their supposed childhood years. Either the photo is mislabeled, or your entire story needs rewriting. That's what Webb is doing to the universe's biography, and the more data it gathers, the harder it is to dismiss as labeling errors. The galaxies, the stars, the black holes, they all point to a universe that evolved faster, earlier, and more energetically than expected, which means our story of the Big Bang, while not wrong in its broad strokes, may be incomplete in its details. The expansion, the cooling, the formation of structures, all may have unfolded in ways we don't yet fully understand. This doesn't mean the Big Bang is overturned. The evidence for a hot, dense beginning and subsequent expansion is overwhelming. The cosmic microwave background, the abundance of light elements, the large-scale structure all confirm it. But what Webb is showing us is that the timeline from that beginning to the universe we know today is not as smooth and predictable as we thought. There are gaps, shortcuts, leaps we can't yet explain. And so cosmologists are once again at the edge of knowledge. They have a framework that works beautifully on large scales, but details at the earliest times are breaking free of the framework. Webb's discoveries are like loose threads, pulling at the weave of the cosmic tapestry. It doesn't unravel the whole picture, but it shows that the stitching near the beginning is different from what we imagined. As the telescope continues its mission, the discrepancies will only grow more precise. Each new observation will either reinforce the need to revise the timeline or provide hints about what mechanisms are missing. For now, we're left with a universe that refuses to stay in the neat boxes we built for it. How do astronomers actually measure these vast distances and times? How do we know that a galaxy is billions of light years away? And how do we translate its faint light into a timestamp on the cosmic calendar? When astronomers look at the universe, they're not just looking at light, they're also looking at how that light has changed during its journey. The concept at the heart of this is redshift, the stretching of light waves as the universe expands. It is the tool that allows scientists to turn faint smudges of light into distances and distances into ages. Without redshift, we would have no way of placing galaxies on the cosmic calendar. It is, quite literally, the dial by which we measure the depth of the universe. The idea is simple in principle, though subtle in practice. Light behaves like a wave with peaks and troughs. The colour of the light depends on the wavelength. Shorter wavelengths correspond to blue and violet, longer ones to red. When an object moves toward you, the waves are compressed, making the light bluer. When it moves away, the waves are stretched, making the light redder. This is the Doppler effect, the same principle that makes the pitch of a passing siren rise and then fall. In astronomy, the effect shows up in spectra as shifts of familiar absorption lines. If the lines appear redder than expected, the object is receding. If they appear bluer, it is approaching. But in cosmology, redshift is more than just motion. It is the expansion of space itself. As the universe grows, it drags light along with it, stretching the waves over billions of years. A photon emitted in the ultraviolet can arrive at Earth as an infrared photon, not because the galaxy was racing away through space, but because the very fabric of space between us has expanded. This cosmological redshift is what makes it possible to look back in time. The greater the redshift, the farther the light has travelled, and the earlier the epoch it reveals. For astronomers, redshift is expressed with the symbol Z. A galaxy at redshift 1 is twice as far in wavelength as it was emitted. Redshift 2 means the wavelength is tripled. By the time you get to redshift 10, the light has been stretched by a factor of 11. Webb is now finding galaxies at redshifts beyond 13, meaning their light has been stretched 14-fold during its journey. Those galaxies emitted their light when the universe was only a few 100 million years old. Without redshift, we would have no way of knowing that. This makes redshift the critical dial on the universe's clock. By measuring it, astronomers can assign ages to galaxies. They can map the cosmic web, trace the growth of structure, and test cosmological models. Every discovery Webb makes depends on understanding redshift accurately. It is how we know that the surprising galaxies, stars, and black holes really do belong to the early universe, and not to some closer, more ordinary epoch. but measuring redshift is not always straightforward. There are two main approaches. The first is spectroscopic redshift, the most reliable. Light from a galaxy is spread out into a spectrum, and astronomers look for characteristic fingerprints of elements, like hydrogen or oxygen. The spacing of those lines reveals how much the light has been stretched. The second approach is photometric redshift, which relies on measuring the brightness of a galaxy in different filters and estimating its distance. Photometric redshifts are faster because you can get them from broad surveys, but they are less precise. Webb uses both methods, but for the most distant galaxies, spectroscopy is key. It provides the hard evidence that a galaxy really is as far away as it appears. Early in Webb's mission, there was some skepticism about whether its faint galaxies truly belonged to such high redshifts. Photometric redshifts suggested they were extremely distant, but skeptics wondered if they might be imposters, closer galaxies with unusual properties mimicking high redshift. Spectroscopic confirmations have since shown that many of these early candidates are indeed genuine. The redshift measurements hold, meaning the galaxies really are that far away, and their light really is that old. Redshift also ties directly to the expansion rate of the universe, the Hubble constant. This is where another tension arises. Different methods of measuring the Hubble constant give slightly different answers. The microwave background suggests one value. Supernova measurements suggest another. Webb's ability to measure redshift at unprecedented distances may help resolve this tension, or it may deepen it by providing new data that doesn't fit either value neatly. Either way, redshift remains the bridge between what we observe and what we calculate. For you listening tonight, think of redshift like listening to an old record player. If the speed of the turntable changes, the pitch of the music changes. In the same way, as space expands, the pitch of light changes. By carefully listening to those shifts, astronomers can tell not only how far away something is, but also how long ago the music of its light began playing. One of the reasons Webb is so powerful is that it is designed to see in the infrared, the very wavelengths into which early light has been shifted. Hubble could see into the near-infrared, but only faintly. Webb goes much deeper, capturing the red-shifted light of galaxies far older than Hubble could reach. This is why Webb is described as a time machine. It doesn't just take sharper pictures, it tunes into a channel of light that carries the oldest messages the universe has to offer. And yet, as fundamental as redshift is, it isn't without complications. Some astronomers wonder if we may be oversimplifying by treating it purely as expansion. Could there be other processes at work in stretching light? For example, interactions with intervening matter or effects of quantum physics at cosmological scales. These ideas are speculative, but Webb's findings keep them alive. When galaxies look older than their redshift should allow, it makes some researchers wonder if our interpretation of redshift itself might need revisiting. Most scientists still trust the standard view, but the fact that Webb has reopened the discussion shows just how disruptive its discoveries are. Redshift also provides insight into another crucial question: how galaxies evolved over time. By comparing galaxies at different redshifts, astronomers can trace their growth across billions of years. Lower redshift galaxies show later stages of evolution, while higher redshift ones show earlier stages. By stitching them together, Webb allows us to build a movie of cosmic history. But the movie is not playing out as expected. The high redshift frames already show galaxies that belong in later scenes. The redshift dial confirms the timeline, but the story unfolding on it does not match the script. This is why Webb's redshift measurements are so vital. They don't just give us numbers, they tell us that the anomalies are real, that galaxies truly did exist when the universe was only a few % of its current age. Without redshift, we could dismiss them as errors. With redshift, we are forced to confront the reality that the universe evolved faster than our models predicted. For cosmology, this is both a challenge and an opportunity. It means that the redshift-distance relationship, one of the pillars of the Big Bang model, is holding firm, but the physical processes tied to those distances may need revision. Galaxies, stars, and black holes were in place earlier than we thought possible. Redshift tells us when they were there. Now the task is to explain how. And this brings us to a deeper point. Redshift doesn't just tell us about galaxies. It tells us about the very expansion of the universe. Every photon Webb captures has been stretched by the growth of space. Every measurement is a direct probe of cosmic history. By mapping redshift across countless galaxies, astronomers can test whether expansion has been constant or whether it has changed in subtle ways. Already, evidence suggests that the expansion rate may not match expectations perfectly. Webb's precision could sharpen those discrepancies, perhaps even pointing toward new physics beyond our current models. So when you hear about redshift, don't think of it as an abstract technical term. Think of it as the universe's distance dial, the way we transform faint light into a story of time. It is how we know that Webb is not just seeing distant galaxies, but ancient ones. It is how we place them on the cosmic calendar, how we trace the arc of history back to the earliest pages. And it is why Webb's discoveries carry such weight. Because the redshifts are real, the puzzles they reveal cannot be ignored. When we look at the galaxies Webb has revealed, we're seeing light that left billions of years ago, light that began its journey long before humans, Earth, or even the Sun existed. But there is light even older than that, light that began its journey before there were galaxies, before there were stars, before there were suns at all. It is the most ancient signal we can detect, and it forms the backdrop to everything else in the universe. This is the cosmic microwave background, the afterglow of the Big Bang itself. To understand why this light is so important, we need to return to the earlier stages of the universe. After the Big Bang, the cosmos was unimaginably hot and dense. Matter and radiation were mixed together in a kind of plasma, with electrons and protons colliding so often that light couldn't travel freely. Photons were constantly scattered, unable to get far without bumping into something. In that state, the universe was opaque, a fog of particles and radiation. No telescope, no matter how powerful, could see through it. As the universe expanded, it cooled. About 380,000 years after the Big Bang, conditions finally changed enough for electrons and protons to combine into neutral hydrogen atoms. Suddenly light could travel unimpeded. The fog lifted. The photons that streamed out at that moment have been travelling ever since, stretched by the expansion of space into microwaves. That faint glow fills the universe even now. It's everywhere in every direction, a relic of the moment the cosmos first became transparent. When radio antennas were first tuned to detect it in the 1960s, scientists were astonished. Here was direct evidence of the Big Bang, a leftover signal from the universe's childhood. In every square of sky, no matter where you looked, the same faint background appeared, uniform to an astonishing degree, with only tiny variations. Those variations, measured later with exquisite precision, turned out to be the seeds of all structure. Slight differences in density in that early plasma grew into the galaxies, stars, and clusters we see today. This is why the cosmic microwave background is often described as a baby picture of the universe. It shows us the cosmos before stars existed, before galaxies formed, before suns lit up. It is light that left before there were any suns at all. Now, where does James Webb fit into this? Webb cannot see the microwave background directly. Its instruments are tuned to the infrared, not to microwaves. But Webb bridges the gap between the microwave background and the first galaxies. It captures the moment when darkness ended and starlight began, the time astronomers call rayonization. By studying the earliest galaxies, Webb connects the afterglow of the Big Bang with the structures that followed. It provides the missing frames in the movie of cosmic history, and what a movie it is! Imagine starting with a frame of a newborn baby, then jumping ahead to a photograph of an adult, and wondering what happened in between. The microwave background is the baby picture, and the modern universe is the adult portrait. Webb supplies the childhood photos, the adolescent years, the transition from blank plasma to blazing galaxies. For the first time, we can watch the story unfold with fewer gaps. This light that predates stars also tells us something profound about the nature of the universe itself. The uniformity of the microwave background shows that the cosmos was smooth at the beginning, with only tiny fluctuations. Without those fluctuations, galaxies could never have formed. Gravity needed seeds to work on, little overdensities to pull matter together. The fact that we see galaxies now means those seeds must have been there, written into the earliest light. Webb's discoveries of mature galaxies so soon after the Big Bang are therefore not just puzzles about time. They are tests of how those early fluctuations grew. If galaxies appeared earlier than expected, maybe the fluctuations were larger, or maybe they grew faster, or maybe something else entirely gave them a boost. There is another way to think of this light. It is a kind of cosmic messenger, carrying information from an era before suns existed. Every photon of the microwave background has travelled across nearly 14 billion years to reach us. In that time, galaxies formed, stars burned, planets were born, life emerged, civilizations rose and fell, and yet the photons kept moving, unchanged except for the stretching of their wavelengths. When we detect them, we are catching messages sent before there were senders, echoes from a universe that had not yet built any of the things we associate with existence. That perspective can be overwhelming. Here we are, listening to signals older than any star, older than any world, older than the elements in our bodies. The calcium in your bones, the oxygen in your lungs, the iron in your blood. All of it was forged in stars that came much later. But the microwave background predates even those stars. It is a reminder that the universe's history stretches far beyond the familiar. For astronomers, comparing the microwave background with Webb's galaxies is one of the most powerful tools available. The background sets the initial conditions. Webb shows the outcomes. If the outcomes don't match what the conditions predict, then something is missing in the middle. That missing piece may be new physics, new processes, or simply a misunderstanding of how matter behaves at extreme scales. Whatever it is, Webb's role is to illuminate it. One of the most striking aspects of this connection is the sense of continuity. The same photons we detect in the microwave background were released when the universe first became transparent. The same photons we detect with Webb from the first galaxies began their journey only a few 100 million years later. Together they bookend the cosmic dark ages, the period when no suns yet burned. With both ends in view, we can finally trace how darkness gave way to light. For you listening tonight, think of this like hearing echoes in a canyon. One echo comes from a voice shouted long ago, still bouncing back across the walls. Another comes from a voice shouted later, clearer, closer. Together they tell you about the shape of the canyon, about how sound travels through it. In the same way, the microwave background and Webb's galaxies tell us about the shape of the universe, about how matter and light move through it across time, and the fact that we can hear both echoes is remarkable in itself. If the universe had expanded just a little differently, the microwave background might have been lost to us. If Webb had not been built, the first galaxies might have remained hidden. The alignment of our time, our technology, and the universe's transparency is a rare gift. We exist in an era when these messages are still detectable, when the universe has not yet stretched them beyond recognition. Billions of years from now, future observers may not be so lucky. The expansion of space will push distant galaxies beyond the horizon. The microwave background will fade. The early light Webb is capturing will slip away forever. That makes our moment in cosmic history unique. We're able to piece together a story that won't always be accessible, and the story is changing as we learn more. For decades, the microwave background seemed to tell a neat tale. Small fluctuations grew into galaxies on predictable timescales. Now, Webb is showing us galaxies that grew faster than those fluctuations alone should allow. The connection is breaking down. The light that left before there were suns is whispering one story, while the galaxy's Webb seas are telling another. Reconciling the two is one of the great challenges of modern cosmology. This doesn't make the microwave background less important. On the contrary, it makes it more crucial. It is the anchor point, the baseline, the cosmic dawn we can measure directly. Webb's role is to show how quickly the universe moved from that baseline to complexity. The tension between the two is where new discoveries will come. When astronomers speak about the origins of the universe, two kinds of evidence often sit side by side. On one hand, there is the cosmic microwave background, the faint afterglow of the Big Bang. On the other, there are the first galaxies and stars revealed by telescopes like James Webb. These two sources of light tell different parts of the story, and comparing them has become one of the most important tests of cosmology. In many ways, the tension between them is where our understanding is now being pushed to its limits. The cosmic microwave background, or CMB, is a snapshot of the universe when it was only 380,000 years old. It shows us a cosmos that was hot, dense, and almost uniform, with only tiny ripples in temperature and density. Those ripples are crucial. They were the seeds of all later structure. Without them, galaxies could not have formed. Observations of the CMB, made with satellites like COBE, SOASMAP, and Planck, have given us an extraordinarily precise picture of the universe's composition and age. The patterns in the microwave background tell us how much dark matter exists, how much dark energy drives expansion, how much ordinary matter makes up stars and gas. They also confirm the timeline of the Big Bang with remarkable accuracy. James Webb, on the other hand, does not see the universe at 380,000 years old. It looks billions of years later, but still at times so early that galaxies had only just begun to form. Its instruments are tuned to infrared, capturing light stretched by expansion from ultraviolet and visible into wavelengths invisible to the human eye. What Webb sees are not seeds, but outcomes: galaxies shining, stars burning, black holes feeding. Where the CMB is a beginning, Webb is the first flowering. In theory, these two views should align. The ripples in the microwave background set the stage, and the galaxies Webb sees should be the natural consequences of that stage. But what Webb has revealed is that the galaxies appear too soon, too large, too developed compared to what the CMB predicts. This is where the comparison becomes so powerful. The CMB says one thing about the early universe's conditions, while Webb shows us results that don't fit neatly with those conditions. To understand why this mismatch matters, it helps to think about the CMB in more detail. The fluctuations it contains are tiny, just one part in 100,000. Yet from those small beginnings, all the structure of the universe emerged. Gravity amplified the fluctuations, pulling matter into clumps, building stars, galaxies, and clusters. The timescale for this growth is encoded in the data. The CMB tells us how long it should take for galaxies of a given mass to appear. When Webb finds galaxies that seem to leap ahead of that schedule, it raises the possibility that something is missing in our interpretation of the CMB. But the CMB is not wrong. Its precision is extraordinary. The data from Planck in particular match theory with exquisite accuracy. So the puzzle becomes, how can both be right? How can the CMB show us a slow, steady growth from tiny fluctuations, while Webb shows us galaxies maturing far earlier than expected? Some scientists propose that the answer lies in the efficiency of star formation. Perhaps once the first clumps formed, they converted gas into stars more quickly than models assumed. That would allow galaxies to grow large sooner without contradicting the CMB. Others suggest that the fluctuations in the CMB, while small on average, may have contained rare peaks, regions where matter was unusually dense, collapsing into galaxies faster. Webb may be especially good at spotting these rare regions because of its depth and sensitivity. Another possibility is that new physics is at play. If dark matter interacts in ways we don't fully understand, it could have accelerated structure formation. If dark energy behaved differently in the early universe, the expansion history might not match our assumptions. Even subtle changes in how gravity operates on large scales could have dramatic effects. Each of these ideas is speculative, but Webb's findings demand speculation. It's important to remember too that the CMB and Webb are observing in completely different ways. The CMB is a global measurement, a broad snapshot of the entire universe at once. Webb is local, targeting specific regions, finding individual galaxies. Reconciling the two means bridging the gap between global averages and local details. Perhaps the universe is more varied, more uneven in its early stages than we realized. Perhaps the galaxies Webb sees are the lucky few that formed in the densest spots, while most of the cosmos matched the slower pace predicted by the CMB. For you listening tonight, it might help to think of this like weather and climate. The climate tells you the average conditions, the long-term trends, the overall picture. The weather tells you what happens in a specific place on a specific day. Sometimes the weather seems to defy the climate. A cold snap during a warming trend, a storm during a calm season. The CMB is like the climate of the early universe, while Webb is reporting on the weather in specific patches of it. The two aren't in contradiction, but they can appear mismatched until we understand how the local fits into the global. And yet, the scale of Webb's discoveries suggests it's not just a few local anomalies. The number of early galaxies it has found is larger than expected. The maturity of those galaxies is more widespread than chance alone would explain. That makes the comparison with the CMB even more pressing. If the CMB gives us the initial conditions, then perhaps those conditions are being interpreted too narrowly. Maybe the seeds it describes were more fertile than we assumed. One particularly intriguing possibility is that the small fluctuations seen in the CMB may not tell the whole story. Inflation, the rapid expansion, thought to have occurred just after the Big Bang, may have left imprints too subtle for the CMB to capture directly but strong enough to affect galaxy formation. If inflation produced regions of enhanced density beyond what we can see in the microwave background, Webb's galaxies might be evidence of them. This is why the partnership between CMB studies and Webb is so powerful. Each probes a different part of the timeline. Together they test the coherence of our models. If they don't match, then something new must be discovered. It may be new physics, new processes, or simply refinements in how we model star and galaxy formation. Whatever the answer, the tension is not a problem to be ignored. It is the frontier where science advances. And beyond the technical, there is something deeply human about this comparison. The microwave background is the oldest light we can see, a message from a time before stars existed. Webb's galaxies are the next chapter, the first signs of cosmic complexity. By holding them side by side, we see the universe both as it began and as it first began to grow. The contrast is striking, from smooth plasma to structured galaxies in less than 500 million years. The fact that we can trace that transformation at all is extraordinary. The fact that it doesn't match our neat expectations is even more extraordinary, because it means there is still more to learn. For cosmologists, this is an exhilarating moment. For decades, the CMB seemed to lock the timeline into place, giving us confidence that the story was mostly complete. Now Webb has reopened the script. The two kinds of light don't quite agree, and in that disagreement lies the promise of discovery. If the CMB and Webb don't align, then models of the universe will need to be adjusted. But what does that adjustment look like? Do we stretch the timeline, tweak the physics, or consider more exotic ideas like cycles, bounces, or even multiverses? When evidence begins to pile up that doesn't quite match our expectations, science doesn't stop. It bends, it stretches, and sometimes it breaks before rebuilding itself. That's where we now find ourselves with James Webb's discoveries. The galaxies that are too large, the stars that are too mature, the black holes that are too massive, and the mismatch with the cosmic microwave background. All of these are small pieces of evidence pointing toward the same unsettling conclusion. Our current theories may be under strain. The question is, are we missing something? To understand the scope of this strain, it's worth remembering just how successful modern cosmology has been. The so-called Standard Model of Cosmology, often referred to as LCDM, standing for Lambda Cold Dark Matter, has explained a remarkable range of phenomena. It describes the expansion of the universe, the distribution of galaxies, the behaviour of dark matter, and the mysterious push of dark energy. It has predicted the abundance of hydrogen, helium, and lithium. It has matched the fine details of the cosmic microwave background. Few scientific models have achieved so much agreement with so much data. That's why scientists trusted it deeply when Webb launched. But Webb wasn't built to confirm what we already knew. It was built to probe the places where our knowledge is thin, the cracks in the story. And it wasted no time in finding them. Theory said the first billion years after the Big Bang would be a time of small, irregular galaxies, slowly gathering mass. Instead, Webb shows galaxies nearly as massive as the Milky Way appearing in that era. Theory said stars without heavy elements, the first generation, should dominate early times, and only later would chemically enriched stars emerge. Instead, Webb finds galaxies with evidence of metals almost from the start. Theory said black holes should take billions of years to reach millions of solar masses. Instead, Webb shows them already feasting in the first few 100 million years. None of these contradictions alone would have been devastating. Every field of science finds anomalies, but taken together, they form a pattern that is harder to dismiss. It isn't a single piece of evidence misinterpreted. It's a consistent theme. The universe was faster, earlier, and more mature than the timeline allows. One way to resolve this tension is to assume that star formation and galaxy growth were simply more efficient than expected. Perhaps our models underestimated how quickly gas could collapse and ignite. Perhaps the feedback processes that slow star formation today, winds from stars, outflows from black holes, were weaker in the early universe. If those checks and balances were less effective, then stars and galaxies could have grown at a breakneck pace. This explanation has the virtue of being conservative. It doesn't throw out the standard model, it just tweaks the details. But efficiency alone may not be enough. Even if star formation were maximised, there are limits set by physics, limits on how fast gas can cool, on how much material can fall into a halo, on how quickly black holes can grow. Webb's discoveries press up against those limits and sometimes burst right through them. That's why some astronomers think efficiency cannot explain everything. There may be something deeper missing. Dark matter is one candidate for revision. In the standard model, dark matter is cold, meaning its particles move slowly compared to the speed of light. This allows it to clump and form the scaffolding for galaxies. But what if dark matter behaves differently? If it interacts more strongly with itself or with normal matter, its structures might have formed sooner, pulling galaxies along with them. There are even proposals for warm dark matter, with slightly faster moving particles that change how small-scale structures form. Webb's galaxies could be the testing ground for these variations. Then there's dark energy, the mysterious force driving the universe's accelerated expansion. In the standard model, it is constant, represented by the Greek letter lambda. But what if it isn't constant? What if dark energy evolved over time, behaving differently in the early universe than it does now? That could alter the expansion history and shift the timeline. Webb's redshift data, combined with other measurements, may provide clues, and then there is the possibility that our very understanding of gravity might not be complete. Einstein's general relativity has passed every test we've thrown at it, from planetary orbits to gravitational waves. But those tests have mostly been within galaxies or clusters, not on the larger scales of the cosmos. If gravity works slightly differently across billions of light years, it could affect how quickly structures form. Alternative theories of gravity exist, though none yet matches the success of general relativity. Still, Webb's discoveries give them new relevance. Some researchers go further, suggesting that the entire framework of LCDM might need rethinking. If the first galaxies are too massive, Maybe the universe is older than 13.8 billion years. A slightly older universe would give galaxies more time to grow. But changing the age isn't simple. It would disrupt the microwave background, the expansion history, and countless other observations. Yet even such radical ideas are on the table, because Webb has made the contradictions so stark. Beyond these adjustments, there are also more exotic proposals. Perhaps the Big Bang wasn't a singular beginning, but a bounce from a previous universe. In that case, structures could have been seeded by physics carried over from before, or perhaps inflation. The rapid expansion just after the Big Bang left imprints stronger than expected, producing regions of unusually high density where galaxies formed early. Some even suggest that primordial black holes, created almost instantly after the Big Bang, seeded galaxies and accelerated their growth. These ideas are speculative, but speculation is often the first step toward discovery. For listeners tonight, imagine trying to piece together a puzzle where most of the pieces fit perfectly, but a handful refuse to click. You press harder, you double-check, but they still don't fit. At first, you assume the puzzle pieces are flawed, misprinted, but then you realize the picture on the box might not match the puzzle inside. That's the position of cosmology now. The box image, the standard model, matches most of the pieces, but Webb's galaxies are pieces that don't fit neatly, forcing us to wonder if the picture needs to change. This moment in science is not one of despair, but of opportunity. Every time a theory has been stretched to breaking, new insights have followed. When Newtonian physics couldn't explain Mercury's orbit, Einstein's relativity emerged. When galaxies appeared to rotate too quickly for their visible matter, dark matter was proposed. When the universe's expansion accelerated, dark energy entered the story. Each strain led to growth. Webb may be opening the door to the next great leap, and yet, scientists are cautious. The telescope is still new, and its data are still being analysed. Spectroscopic confirmations of the earliest galaxies are ongoing. Some candidates may turn out to be closer than they appear. Models of star formation in the early universe are still being refined. It's possible that some of the anomalies will shrink with better understanding. But even if they do, enough tension remains to demand attention. This tension is what drives science forward. It is not enough to say the theory mostly works. The mismatches are where progress hides. That is why Webb is so powerful. It doesn't just confirm what we know, it forces us to confront what we don't. For ordinary people listening in the quiet of the night, this may sound like uncertainty, but it is actually a sign of strength. Science doesn't cling blindly to its models. It tests them, challenges them, and reshapes them when evidence demands. Webb's discoveries are evidence demanding a response. Whether that response is small adjustments or sweeping revisions, it will deepen our understanding of the cosmos. If the standard timeline is strained, one possible solution is to change the age of the universe itself. Could it be older than we think? Could those early galaxies and black holes simply have had more time than the standard model allows? For more than 2 decades, cosmologists have spoken with unusual confidence about the age of the universe. 13.8 billion years has been the accepted figure, derived from precise measurements of the cosmic microwave background, the expansion rate of galaxies, and the abundance of light elements. It's a number repeated in textbooks, documentaries, and classrooms around the world. Yet now, with James Webb's discoveries, the certainty of that number has begun to feel less solid. The sight of massive galaxies and black holes so early in cosmic history has raised an uncomfortable question. Could the universe be older than we think? The standard age is not arbitrary. It comes from carefully fitting together multiple lines of evidence. The cosmic microwave background provides a baby picture of the universe, and by analysing its patterns, scientists can determine the age of the cosmos with remarkable precision. The Hubble constant, which measures how fast galaxies are receding, offers another check. Stellar evolution, the life cycles of the oldest stars, provides yet another. When all of these methods are combined, they converge on about 13.8 billion years. That convergence has been one of cosmology's greatest successes. But Webb has revealed galaxies that appear too mature, too massive, too soon for that timeline. If the age of the universe were greater, those galaxies would have had more time to form, and the problem would be less severe. Some researchers have floated the idea that perhaps the universe is older than 13.8 billion years, maybe by hundreds of millions or even a billion years. That extra time could explain why galaxies and black holes seem so developed in Webb's early snapshots. At first glance, this seems simple. If your train arrives earlier than expected, maybe your watch is wrong. If galaxies are older than the model predicts, maybe the universe is older too. But science is rarely that straightforward. Adjusting the age of the universe means adjusting everything else with it, and that isn't easy. For one, the microwave background is exquisitely consistent with the 13.8 figure. Its tiny fluctuations match predictions almost perfectly. If the universe were older, those fluctuations would look different. The balance of light elements forged in the first minutes after the Big Bang also points to a young universe, not an older one. To make the universe older, you would have to change the physics of those early processes, and that risks unravelling the model's successes elsewhere. Another complication comes from the so-called Hubble tension. Different methods of measuring the expansion rate of the universe give slightly different answers. Measurements from the microwave background, which look far back in time, suggest one value. Measurements from supernovae and Cepheid stars in the nearby universe suggest another slightly higher value. This discrepancy has been troubling cosmologists for years. If the expansion rate is higher, the universe would be younger. If it's lower, the universe would be older. Webb's discoveries of early galaxies have added another layer to this puzzle, because they seem to point toward the need for more time rather than less. Some scientists suggest that the solution might not be changing the age outright, but changing how we interpret redshift and distance in the early universe. If the expansion rate wasn't constant, if it varied more dramatically in the past, then galaxies might appear younger or older than they really are. Adjusting that could shift the apparent age without rewriting the entire cosmological model. Others think new physics, such as evolving dark energy or exotic forms of matter, might reconcile the discrepancies. Still, the idea of an older universe remains tantalizing. It offers a straightforward way to explain why Webb sees mature galaxies so early. Instead of compressing billions of years of evolution into a few hundred million, we simply allow the universe more time. It's not the most widely accepted solution, but it's one of the simplest to imagine. For those listening tonight, it might help to picture this as reading a book. You're told the book has 300 pages. You flip through and find events on page 20 that don't belong there. They're more appropriate for page 50. At first, you think it must be an error in printing, but then you wonder if the book actually has more pages than advertised. Maybe what you thought was page 20 is really page 30, and the numbering was off. That's the temptation of the older universe idea. It would mean the cosmic numbering system needs adjusting, giving more space for events to unfold. The catch is that the numbering system is tied to very solid observations. The cosmic microwave background is like the page numbers printed directly by the publisher. They are difficult to change. If you adjust them, the entire book risks going out of sequence. That's why many cosmologists resist the older universe explanation. It would solve one problem but create many more. Even so, the possibility lingers. Webb's galaxies are not going away. They are being confirmed, not dismissed. Each new deep field strengthens the case that something is off with our understanding. If it isn't efficiency, if it isn't feedback, if it isn't hidden errors in measurement, then perhaps the age really does need reconsideration. There's also a philosophical angle to this. For centuries, humans believed the universe was eternal. Only in the 20th century did we accept that it had a beginning, that it was finite in age. That shift was revolutionary. If Webb's discoveries now suggest that our age estimate is off, even by a modest amount, it would be a humbling reminder that our grip on cosmic time is still provisional. We've moved from infinity to billions of years, and perhaps now to billions plus a little more. Each step refines the picture, but each step also shows how much remains uncertain. For astronomers, this uncertainty is energizing. It means the story is still being written. If the universe is older, even slightly, then our understanding of galaxy formation, stellar evolution, and cosmic history must shift to accommodate it. New observations, new simulations, and new theories will be needed. Webb is not just showing us light. It is showing us the limits of our confidence. And whether the universe is 13.8 billion years old, or 14, or something else entirely, the bigger truth remains: it is ancient beyond human comprehension. The difference between 13.8 and 14 may seem vast to astronomers, but to us it is still a span that dwarfs our lives a millionfold. What matters is not just the number, but what the number tells us about the universe's behaviour. And Webb is telling us that behaviour may not be as simple as we thought. When the James Webb Space Telescope revealed galaxies, stars and black holes that seemed to develop too soon, the first instinct of astronomers was to adjust the details of existing models. Maybe star formation was faster than we thought. Maybe dark matter clumped more efficiently. Maybe feedback processes behaved differently in the early universe. These explanations are cautious, keeping the standard picture intact while stretching it to fit the new data. But when the anomalies persist, more exotic ideas begin to re-emerge. Ideas that once lived at the margins of cosmology start to feel worth reconsidering. Cycles, bounces, and multiverses, concepts that stretch beyond the familiar Big Bang story, now hover quietly in the conversation. The traditional Big Bang model describes the universe beginning from a hot, dense state, about 13.8 billion years ago. Space, time, energy, and matter all emerged, expanding outward ever since. That model has been enormously successful. It explains the cosmic microwave background, the abundance of elements, and the large-scale structure of galaxies. But it has always left a few questions unanswered. What happened at time zero? Why was the universe so uniform at large scales? What set the initial conditions that allowed galaxies to form? Inflation was added to address some of these puzzles, describing a burst of exponential expansion in the first fraction of a second. Yet even inflation raises new questions like what started it and what stopped it. This is where alternative models come in. One of the oldest is the idea of a cyclic universe. Instead of a single beginning, the universe may go through endless cycles of expansion and contraction. In such a scenario, what we call the Big Bang is just the latest rebound in an infinite sequence. When one universe ends in a crunch, another begins with a bang. This idea has a certain elegance. It removes the need for a true beginning. It also offers a way to explain why the universe looks so uniform, since each cycle could wipe the slate clean before starting again. If the universe is cyclic, then Webb's discoveries of early galaxies might fit into a broader picture. Perhaps structures are seeded by remnants of previous cycles, allowing them to form faster in the next. That would explain why galaxies look so mature so early. Evidence for cycles is hard to find, though. The traces of previous universes, if they exist, would be subtle, possibly hidden in the microwave background or in patterns of gravitational waves. Webb itself may not be able to prove or disprove this, but the fact that we're even revisiting the idea shows how unsettling its data has been. Closely related is the concept of a bounce. In some models, the Big Bang wasn't a creation from nothing but a bounce from a collapsing state. Instead of an absolute beginning, there was a contraction phase before the expansion. The universe shrank, reached a minimum size, and then rebounded. Such models avoid the singularity problem, the infinite density at time zero that general relativity cannot handle. A bounce could also provide seeds for early structure, passing information from the contracting phase into the expanding one. If that's true, then the galaxies Webb is finding may not be anomalies at all. They may be natural consequences of a universe with a history longer than we thought. Then there is the idea of the multiverse. In some versions of inflation, the rapid expansion never ends everywhere at once. Instead, it continues in some regions while stopping in others, creating pocket universes with different properties. Our universe would just be one bubble in a vast cosmic foam. In such a picture, the conditions we observe are not unique. Other universes might have different physical laws, different constants, even different numbers of dimensions. The multiverse is a controversial idea because it's difficult to test, but Webb's discoveries give it a renewed edge. If our universe shows properties that seem unlikely or fine-tuned, like galaxies forming too quickly, one explanation could be that we're in a universe where conditions happen to favour rapid structure. In another bubble, perhaps they didn't. For many scientists, these exotic ideas feel like last resorts. They prefer to adjust models within the Big Bang framework rather than leap to cycles or multiverses, but science is also about openness. If the evidence continues to press against the boundaries, then even radical possibilities must be considered. Webb doesn't prove these ideas, but it has created the space for them to be discussed more seriously. For those listening tonight, it might help to think of it like this. Imagine you're reading a story. At first, it seems straightforward, with a beginning, middle, and end. But as you go deeper, you discover clues that don't fit the timeline. Characters appear before they're introduced. Events happen out of order. You can try to adjust the details, but eventually you might wonder if the story is part of a larger series, or if the book has been looping back on itself. That's what these exotic ideas represent. Different ways of imagining the cosmic narrative. There are also more speculative versions. Some theories suggest that the universe has higher dimensions beyond the 3 of space and 1 of time we experience. Our universe could be a brain, a kind of sheet floating in a higher dimensional space, occasionally colliding with other brains. Such collisions could trigger bangs and bounces, seeding new universes. Others suggest that quantum fluctuations at the smaller scales might spawn entire universes, each with its own rules. These are bold ideas, and for now they live at the edges of theory. But Webb has reminded us that the edges are where surprises come from. And there's another layer. Exotic models don't just explain anomalies, they also touch on some of the deepest philosophical questions humans have ever asked. Was there a beginning? Will there be an end? Are we unique, or is reality filled with countless universes, each with its own story? Webb isn't designed to answer those questions directly, but by showing us galaxies and stars that don't fit our neat timeline, it forces us to keep asking. The anomalies are not proof of cycles, bounces, or multiverses, but they are invitations to think bigger, to consider possibilities beyond what we once thought safe. One of the most exciting aspects of this moment in science is that all these ideas, cycles, bounces, multiverses, are being revisited not in the abstract but in response to real data. They are not just armchair speculations anymore. They are attempts to explain what Webb is actually seeing. That's what makes them worth exploring seriously. If galaxies look older than the universe should allow, then something extraordinary must be happening. Whether it's new physics, a revision of time, or a whole new framework, the conversation is open, and Webb is not working alone. Future observatories will build on its discoveries. Telescopes studying gravitational waves may detect signals from the earliest times, perhaps even from a bounce or a previous cycle. Experiments on Earth may probe dark matter and dark energy, testing whether they behave as the standard model assumes. Each line of evidence will add weight one way or another. Webb has opened the door, others will step through it. For now, we stand at the threshold. The familiar models are straining, the anomalies are real, and the possibilities range from subtle adjustments to revolutionary shifts. That's the beauty of this moment. The universe has reminded us that it is not simple, not fully mapped, not yet contained by our equations. When scientists try to understand why the universe looks the way it does, they can't rely only on the matter we see. Stars, planets, gas clouds, and galaxies make up only a small fraction of what's really there. The rest, the dominant majority, is hidden from view. We call it dark matter and dark energy. These two invisible components are central to the standard model of cosmology, and they play a decisive role in explaining how structures grow and why the expansion of the universe behaves the way it does. When James Webb started returning data that didn't match expectations, galaxies too large, black holes too massive, stars too developed, attention naturally turned to these unseen actors. Could dark matter and dark energy be responsible for the surprises? Dark matter came into the story nearly a century ago, when astronomers noticed that galaxies were rotating too quickly. The stars at the edges should have flown off into space if only visible matter were holding them together. Something unseen had to be adding gravitational pull. Later, studies of galaxy clusters and gravitational lensing confirmed it. Whatever dark matter is, it outweighs ordinary matter by a factor of about 5 to 1. It doesn't emit or absorb light, but its gravity sculpts the cosmos. It forms halos, invisible structures that act as cradles for galaxies. Without dark matter, galaxies as we know them couldn't exist. Dark energy is an even stranger player. It entered the picture in the late 1990s, when astronomers discovered that the expansion of the universe is accelerating. Instead of slowing down under gravity, galaxies are receding faster and faster. The best explanation is a mysterious form of energy filling space itself, pushing it outward. Dark energy now accounts for about 70% of the universe's content. Its nature remains elusive, but its effects are undeniable. Together, dark matter and dark energy dominate the universe. Yet we know almost nothing about what they actually are. We describe their behavior mathematically, but their physical reality is still hidden. This makes them natural candidates whenever anomalies appear. If galaxies look too mature too soon, maybe dark matter behaved differently in the early universe. If the timeline seems off, maybe dark energy has not been constant, but has evolved. Webb's discoveries, by straining the standard model, bring these questions back to the forefront. Start with dark matter. In the standard picture, cold dark matter clumps early, creating gravitational wells where gas can gather to form stars. The cosmic microwave background tells us about the distribution of these initial clumps. Simulations then show how galaxies should grow inside them, but Webb finds galaxies that grew faster than those simulations allow. One way to explain this is to propose that dark matter clumped even earlier or more efficiently than expected. Perhaps its particles interact in ways we haven't accounted for, allowing halos to form quickly and giving galaxies a head start. Some scientists have suggested warm dark matter as an alternative. Instead of particles that move slowly, warm dark matter would have slightly higher velocities. This changes how small-scale structures form, suppressing some while enhancing others. If Webb's galaxies represent unusual peaks seeded by such effects, then warm dark matter might explain them. Others explore self-interacting dark matter, particles that collide with each other more often than in the cold model. Such interactions could alter halo formation, making galaxies emerge sooner. Webb's data doesn't settle these debates, but it gives new urgency to them. Dark energy, meanwhile, shapes the overall expansion. In the standard model, it is represented by the cosmological constant, a uniform pressure that doesn't change with time. But what if dark energy isn't constant? If it was weaker or stronger in the early universe, the expansion rate could differ, altering the timeline. Galaxies might then have more time to grow than we thought, or appear at redshifts that don't match our expectations. Some researchers propose dynamic dark energy, where its effects evolve over cosmic history. Webb's precise redshift measurements could help test this by showing whether expansion matches the predictions of a constant dark energy or deviates in subtle ways. The role of dark matter and dark energy also extends to the reionization era, the time when the first galaxies and stars ionize the hydrogen fog. If galaxies were abundant early, as Webb suggests, then reionization may have happened faster than predicted. That in turn depends on how dark matter and dark energy shape the growth of structures and the expansion of space. Understanding their roles isn't just about reconciling models with Webb's anomalies, it's about piecing together the entire history of the universe's transformation from darkness to light. For listeners tonight, imagine trying to build a city on a landscape you can't see. The visible buildings are only a fraction of the story. Beneath them are foundations and supports you don't fully understand, but without them the city couldn't stand. Dark matter is those hidden foundations, holding galaxies together. Dark energy is like the shifting ground beneath everything, controlling how far apart the buildings drift. Webb's discoveries show the city is growing differently than we expected, so naturally we have to ask whether the hidden foundations or the shifting ground are responsible. It's worth remembering that both dark matter and dark energy were introduced to explain anomalies. Dark matter came about because galaxies weren't rotating as they should. Dark energy came about because the universe was expanding faster than it should. In both cases, rather than discarding the broader models, scientists added new components to make the equations work. Webb's data may be pushing us toward a similar moment. If galaxies are too mature too soon, maybe we need another adjustment, another hidden factor. Or maybe we need to revisit what we already believe about dark matter and dark energy. Some theorists go even further, suggesting that what we call dark matter and dark energy might be aspects of a single, deeper phenomenon. Perhaps they are different manifestations of one underlying field, one that governs both attraction and repulsion in the cosmos. If Webb's anomalies point to cracks in the distinction, it could hint at a unifying principle we have not yet uncovered. What makes this particularly challenging is that Webb itself cannot detect dark matter or dark energy directly. It sees their effects indirectly, in the distribution of galaxies, in the rate of growth of structure, in the redshift of distant light. To truly probe them, we will need to combine Webb's observations with other data, gravitational lensing surveys, cosmic microwave background studies, experiments searching for dark matter particles, and projects measuring the expansion rate of the universe with extreme precision. Webb is one piece of a larger puzzle, but it is a critical piece because it probes timescales we could not reach before. The strain on theory is already clear. If dark matter and dark energy behave exactly as the standard model assumes, then galaxies should not look the way Webb sees them. That means one of two things. Either our models of normal matter, gas, stars, black holes, are incomplete, or our understanding of the dark components is incomplete. Either way, the invisible majority of the universe is back at the centre of debate. And there's something humbling in this. We live in a universe where 95% of the content is invisible and unknown. Dark matter and dark energy dominate everything, yet we only see their shadows. Webb's discoveries remind us how precarious our understanding is. We have equations, we have simulations, but when new light arrives from the edge of time, it reveals just how provisional our knowledge remains. This is not discouraging. It is the lifeblood of science. Each anomaly is a clue. Each surprise is a doorway. If Webb is telling us that dark matter and dark energy are more complex than we thought, then the coming decades will be an era of exploration not just in space, but in fundamental physics. New theories, new experiments, new technologies will all be part of the search. Behind every telescope image, every equation, and every headline about the cosmos are people. Human beings with their curiosity, their disagreements, their long hours, their flashes of excitement, and their moments of deep doubt. The James Webb Space Telescope may be a machine floating far beyond the Earth, but its discoveries ripple back into the lives of thousands of scientists around the world. When those scientists look at Webb's data and see galaxies that shouldn't exist, black holes that shouldn't be there, or stars that shouldn't have formed so quickly, they don't just see anomalies, they feel the weight of a puzzle pressing against decades of knowledge. Science is often portrayed as a realm of certainty, a collection of facts handed down from experts. But in reality it is messy, full of debate and revision. Scientists don't always agree, and when Webb's first results began to arrive, that reality became clear. Some astronomers were thrilled, describing the findings as revolutionary, the start of a new era. Others were cautious, reminding their colleagues that early data can be misleading, that redshift measurements needed confirmation, that interpretations could change. There were lively discussions at conferences, heated exchanges in academic papers, and quiet reflections in offices late at night. Imagine what it must feel like to dedicate years of your life to building models of the early universe, only to see them shaken within weeks of Webb's first observations. For some, it must have been exhilarating, the kind of shake-up that makes science thrilling. For others, it must have been unsettling, a reminder that the ground beneath even the most established ideas can shift. This is the human side of cosmology. People grappling with the unknown, balancing excitement with skepticism, driven by the same curiosity that keeps us all awake when we stare into the night sky. There are graduate students analysing spectra, trying to determine if a faint signal really does come from a galaxy 13 billion light-years away. There are senior scientists with decades of experience debating whether Webb's findings demand rewriting textbooks or just revising parameters in existing models. There are engineers who spent years making sure Webb could even survive launch, watching now as the data vindicates their work. And there are theorists scribbling on chalkboards, running simulations, wondering if new physics is required. Each of them is part of a sprawling human network bound together by the pursuit of understanding. It's easy to forget how much emotional labour goes into this. Scientists are trained to be objective, but they are also human. They feel pride when their predictions are confirmed, and frustration when the data refuses to cooperate. They feel the sting of criticism when colleagues disagree, and the rush of joy when a new idea sparks recognition. Webb's surprises have triggered all of these emotions. Some researchers feel vindicated. Those who had argued for years that the early universe might be more complex than models suggested. Others feel the strain of seeing their carefully crafted theories challenged. But in that tension lies progress. The human side is also one of collaboration. Webb's mission is global, with contributions from NASA, the European Space Agency, and the Canadian Space Agency, as well as institutions around the world. Scientists from different cultures, languages, and backgrounds all share the same data, often in real time. They gather in online meetings, compare notes across continents, and release results that are pored over by colleagues everywhere. It is a reminder that the pursuit of cosmic knowledge is not bound by national borders. The universe belongs to all of us, and so does the effort to understand it. And yet, collaboration doesn't erase competition. Scientists still race to publish papers, to interpret Webb's findings first, to have their names attached to discoveries. When a new data set is released, research groups rush to analyse it, sometimes reaching different conclusions from the same numbers. Disagreements can be sharp, but they are part of the process. Through argument and counter-argument, ideas are tested and refined. Webb has sparked a flurry of publications, each offering explanations, each staking a claim. It is messy, but it is also how knowledge grows. For those listening tonight, it may be comforting to know that even experts wrestle with uncertainty. They don't have all the answers, they disagree, they get things wrong. But they also learn, adapt, and correct themselves. That humility is built into science, and Webb is putting it on display. When galaxies defy the timeline, scientists don't hide the problem. They confront it, argue about it, and work to solve it. That honesty is what makes progress possible. There's another part of the human side that often goes unnoticed: patience. Webb's results arrive slowly after careful calibration, data reduction, and analysis. Astronomers spend months working on a single spectrum, checking for errors, confirming their methods. Behind every headline about a shocking discovery are countless hours of painstaking work by people who may never be named in the news stories. The telescope itself may orbit silently, but on Earth, Countless eyes and hands are working tirelessly to make sense of what it sends back. And then there's the joy. For many scientists, seeing Webb's first images was an emotional experience. Some cried, some laughed, some sat in silence, overwhelmed. After decades of planning, after countless setbacks and delays, after years of skepticism that Webb would ever launch successfully, the telescope not only worked but exceeded expectations. That moment of triumph was deeply human, a collective sigh of relief and a surge of pride. Every anomaly since then has been a bonus, a reminder that the risk was worth it, that the universe still has secrets to share. The human side also includes the public. Webb's images have captured imaginations worldwide, spreading across social media, printed in newspapers, projected in planetariums. People who may never read a scientific paper have still felt awe at the Golden Telescope's view of distant galaxies. And as those galaxies reveal puzzles, the public becomes part of the conversation. Questions like, could the universe be older? Or, are we missing something? Enter everyday speech. In that way, the mysteries belong not only to scientists but to all of us. But with public attention comes pressure. Scientists know their words will be scrutinized, their ideas amplified or dismissed. Some worry about overhyping anomalies before they're confirmed. Others worry about losing public interest if the puzzles turn out less dramatic than headlines suggest. Balancing caution with curiosity is not easy, yet it is part of the responsibility of working with a telescope like Webb, whose discoveries are too important to stay hidden in academic journals. This human dimension, the pride, the doubt, the collaboration, the competition, the patience, the joy, and the responsibility, shapes how science unfolds. Webb is not just a machine, it is a mirror reflecting human ambition and fallibility. When it shows us galaxies that defy explanation, it also shows us ourselves, struggling to understand, reaching beyond what we know, refusing to settle for easy answers. And as we continue this story, it's worth remembering that science is not finished. Webb is still at the beginning of its mission. The people interpreting its data are still learning how to use it, still building confidence, still refining their tools. The puzzles may deepen or shift as more data arrives. New ideas will rise, old ones will fall. Scientists will argue, collaborate, and wrestle with the unknown. That wrestling is not a weakness. It is the heart of discovery. What does it mean for all of us to live in the Webb era of discovery? How does seeing galaxies at the edge of time change our collective sense of place in the cosmos? The launch of the James Webb Space Telescope didn't just change astronomy, it changed the era we live in. Every generation has its defining instruments, the tools that stretch the boundaries of knowledge and show us reality in ways our ancestors couldn't imagine. For centuries it was Galileo's small telescope, turning blurry points of light into worlds with moons and craters. Then it was Hubble, pulling back the curtain on galaxies beyond count, reshaping our sense of scale. Now it is Webb, looking deeper, sharper, and older than anything before, revealing not only what we expected but what we did not. And in that sense, Webb is not just a telescope. It is a mirror showing us our place in the unfolding story of discovery. Living in the Webb era means that we are the first humans to witness light from galaxies formed just a few 100 million years after the Big Bang. No other generation has had access to such direct evidence of the universe's earlier structures. Our ancestors looked at the night sky and told stories of gods, heroes, and animals. They charted constellations and navigated oceans. We look at the same sky and now see billions of galaxies stretching across cosmic time. But unlike any who came before, we can trace that light to its origin, see its structure, measure its age, and compare it with models of physics. That leap is profound. It also places us in a rare window of cosmic history. The universe is still transparent enough that we can detect the microwave background, still expanding at a pace that allows us to see galaxies billions of light years away. billions of years from now, cosmic expansion will carry many galaxies beyond the horizon of detectability. Future astronomers, even with tools more advanced than Webb, may never see what we can see today. That means we live in a privileged era, uniquely positioned to study the beginning of time itself. Our place in the Webb era is also cultural. These images and discoveries don't belong only to scientists, they belong to everyone. When Webb's first deep field was revealed, showing thousands of galaxies in a patch of sky smaller than a grain of sand held at arm's length, people across the world reacted with awe. It didn't matter whether they understood redshift, cosmology, or dark matter. What mattered was the visceral sense of scale, the reminder that the night sky is more than dots of light. It is an ocean of worlds, and we are afloat within it. That cultural resonance is powerful. It means Webb is not just shaping textbooks, but shaping imaginations. Children growing up today will see its images in classrooms, planetariums, and science museums. They may be inspired to become astronomers, physicists, or engineers. Or they may simply carry a deeper sense of wonder into their lives, knowing that the universe is larger, older, and stranger than they once thought. In that way, Webb becomes part of our shared heritage, like the cave paintings of early humans who looked at the stars and tried to capture them on stone. At the same time, the Webb era reminds us of the fragility of progress. The telescope almost didn't happen. It was delayed for years, its cost ballooned, and more than once it was nearly cancelled. Thousands of people worked tirelessly to solve problems, redesign components, and keep the mission alive. Its success is not just technological, it is human determination at its best, a story of persistence against odds. Our place in this era is possible because generations of people refuse to give up. That too is part of the legacy. The Webb era also forces us to grapple with humility, seeing galaxies that shouldn't exist, stars that seem too mature, and black holes that grew too fast reminds us that our theories, however elegant, are provisional. The universe doesn't bend to our expectations. It reveals itself on its own terms. Living in this era means living with uncertainty, accepting that what we thought was settled may not be, that humility is not a weakness, it is the starting point of wisdom. There is also responsibility. Webb is not only looking at the early universe, it is studying exoplanets, atmospheres, and the chemistry of distant worlds. It may give us our first real evidence of habitability elsewhere. That possibility carries cultural weight. The generation that sees biosignatures in an alien atmosphere will be forever marked by that discovery. Our place in this era may be remembered not only for galaxies at the edge of time, but for the first hints that life is not unique to Earth. For those listening now, think about what it means to be alive at this moment. To sit in the dark, hearing about galaxies whose light has travelled for more than 13 billion years, and to know that your generation is the first to see them. To know that human ingenuity has built a machine that can catch those photons, focus them, and deliver them to Earth as images and spectra. This is not an abstract achievement. It is part of your own lifetime, part of the shared story of humanity. We often think of history as wars, politics, or inventions, but history is also this, the moment when human eyes through a telescope first saw the infancy of the cosmos. Our place in the Webb era is not just observational, it is participatory. The data is public, accessible to scientists worldwide. Papers are uploaded online, debates happen in real time, and the public can follow along almost as events unfold. That openness is new. In past centuries, discoveries were confined to elite groups, slow to spread. Today, an image released by Webb can circle the world in hours, sparking conversation across languages and cultures. In that sense, the Webb era belongs to all of us, not just to experts. And yet, there is something intimate about it too. To look at Webb's images alone at night in silence is to feel a personal connection with the universe. It's not only about collective knowledge, it's about individual perspective. Each of us can look at those galaxies and feel both small and vast, insignificant in scale, yet significant in awareness. Our place in the Webb era is not only defined by what we learn, but by how we feel when we confront that immensity. What comes next in this era will depend on how we respond to the puzzles Webb has revealed. Do we adjust our theories cautiously, or do we embrace radical new ideas? Do we refine the role of dark matter and dark energy, or do we explore cycles, bounces, and multiverses? Our place is not just to observe, but to decide which paths of thought we follow. That decision will shape not only science, but culture, because the stories we tell about the universe shape the stories we tell about ourselves. In the end, to live in the Webb era is to be reminded of two things at once: the vastness of the cosmos and the power of human curiosity. We are small creatures on a small planet, yet we have built a telescope capable of looking back to the dawn of time. That act places us in a unique position, both humble and extraordinary. And as Webb continues to send back light from the edge of the universe, our place in this story will keep unfolding. When we think about science, it is tempting to imagine it as a process of eliminating mystery, replacing the unknown with the known, filling in blank spaces until the picture is complete. But the truth is more subtle. Each time we reach an answer, it opens up new questions. Each time we solve a puzzle, we discover two more hidden beneath it. And with the James Webb Space Telescope, that truth has become more obvious than ever. The galaxies that shouldn't exist, the stars that seem too mature, the black holes that form too soon. These aren't just technical challenges, they're reminders that mystery is not a failure. It is part of the fabric of discovery. Living in this time means living in the tension between knowledge and ignorance. On one hand, we know more about the universe than any humans before us. We can measure the age of the cosmos, detect exoplanets orbiting distant suns, map dark matter through gravitational lensing, and trace the expansion of space itself. On the other hand, the more we know, the more we realize how much remains hidden. Dark matter and dark energy dominate the universe, yet we don't know what they are. Inflation is supposed to explain the early cosmos, yet we don't know how it began. And now Webb shows us galaxies that defy the neat timeline we thought we understood. For many people, that uncertainty might feel unsettling. If science cannot give us definite answers, what does that mean? But for astronomers, and for anyone who lets curiosity guide them, the uncertainty is a gift. It means the universe is still alive with discovery. It means there are still frontiers to explore, still questions that make us wonder. It means that mystery is not something to fear, but something to embrace. There is a kind of comfort in knowing that the universe is not simple. If it were, if we had already mapped every detail, the story would be finished. Instead, we find ourselves in the middle of a grand narrative, one that is still unfolding. Webb's surprises are not the end of knowledge, but the continuation of it. To live in this moment is to live with wonder intact. Wonder at its core is the recognition of vastness beyond comprehension. When you look at Webb's images and see thousands of galaxies in a patch of sky the size of a grain of sand, you feel that vastness. When you hear that some of those galaxies existed less than 1 billion years after the Big Bang, you feel it again. And when you learn that their existence challenges the very models we built to explain them, the wonder deepens. It is not only the beauty of the images, but the mystery behind them that moves us. There is also something deeply human about wonder. It connects us across time. Our ancestors looked at the stars with awe, not knowing what they were. We look at galaxies with awe, knowing more than they did, but still humbled by how much lies beyond. The feeling is the same. It is the bridge between curiosity and humility, between knowledge and imagination. Mystery, too, has its own kind of comfort. We often think of comfort as coming from certainty, from having answers. But there is another kind of comfort that comes from admitting we don't know everything. It frees us from the illusion of control, reminding us that we are part of something larger. It invites us to live with questions, to find peace in the unknown rather than fear. Webb's discoveries invite that kind of comfort. They tell us that the universe is bigger than our equations, richer than our models, and more surprising than we expect. And instead of that being discouraging, it can be reassuring. For those listening tonight, imagine sitting by the ocean. You can measure the tides, chart the currents, predict the waves. But no matter how much you learn, the ocean remains vast, mysterious, and beyond total grasp. That mystery doesn't diminish its beauty. It enhances it. The universe is the same. Webb lets us measure it, but it also shows us how deep and endless it remains. Scientists themselves often speak of this comfort. Behind their equations and data, many admit to a quiet sense of awe, even gratitude, that the universe refuses to be simple. Some describe it as humbling, others as inspiring. They may argue fiercely about models, but they share a common understanding. The mysteries are what make the work worthwhile. If everything fit neatly, there would be no reason to keep looking. The discomfort of not knowing is what keeps the search alive, and that search is not just for scientists. Wonder and mystery belong to all of us. When Webb's images spread across the world, people from every culture and language felt the same pull. You don't need to understand redshift or dark energy to feel the mystery of a galaxy that existed billions of years ago. You don't need equations to feel awe at light that began its journey before Earth was formed. Mystery is democratic. It requires no credentials. It only requires openness. There is also a personal dimension. In moments of uncertainty in our own lives, it can be reassuring to know that even the universe is full of unanswered questions. If galaxies can defy expectations, perhaps our own paths don't need to be so certain either. If scientists can live with not knowing, perhaps we can too. The cosmos becomes a mirror, reflecting not only its vastness, but our own human need to find meaning within it. And Webb has made this mirror sharper. It shows us details we could not see before, but in those details it reveals new puzzles. It reminds us that knowledge and mystery grow together. Each discovery is both an answer and a new question. Each solved puzzle opens a new box. The comfort is not in finishing the search, but in knowing the search will never end. For humanity as a whole, this means our place in the universe is not to master it completely, but to live within its mystery, to measure, to explore, to question, but also to wonder. The Webb era is not only about data, it is about rekindling that sense of awe, reminding us that even in an age of satellites, algorithms, and precision, the universe can still surprise us. And this leads naturally to a final reflection. If wonder and mystery are not failures but gifts, then perhaps the vastness of the cosmos is not something that diminishes us, but something that enriches us. Webb's discoveries are not just about distant galaxies, they are about us, about how we see ourselves in relation to the infinite, and in that relation there is both humility and comfort. When we spend time with the discoveries of the James Webb Space Telescope, it can feel overwhelming. Galaxies stretching back more than 13 billion years. Light that began its journey before the Earth formed. Stars, black holes, and structures that challenge the very models we thought we understood. The scale is so immense that it can leave us breathless, almost lost in the immensity. But within that immensity lies a kind of solace, a reminder that the universe is vast, and in its vastness so too are we. To sit with this thought, let's return for a moment to those deep fields Webb has shown us. Tiny patches of sky, smaller than the space behind your fingernail held at arm's length, filled with thousands of galaxies, each one containing hundreds of billions of stars, each star with the potential for planets, each planet with the potential, however small, for life, and all of it contained in a fraction of the sky. If you looked in every direction, the count would multiply endlessly. We live inside an ocean of worlds, far beyond numbering, far beyond full comprehension. It might be easy, when faced with such immensity, to feel small, and in a way we are. The Earth is a pale dot circling an ordinary star in the outskirts of a galaxy among billions. Our lifespans are fleeting, a blink against cosmic time, But the very fact that we can notice this, that we can see the galaxies, measure their light and ask questions about their origins, gives us a kind of vastness of our own. Awareness is not small. Curiosity is not small. The ability to hold the universe in our minds, even imperfectly, is a vastness unique to us. When Webb shows us galaxies that defy our models, it is not just showing us the universe, it is showing us our own courage to face the unknown. We could ignore the puzzles, cling to old certainties, and pretend we already understand. But instead, we confront them, question them, and accept that we may need to change. That willingness to live with uncertainty, to grow with discovery, is itself a reflection of the universe's vastness within us. Think for a moment of the photons Webb collects. Each one travelled across billions of years, across space that has been stretching the whole time, across galaxies colliding and stars exploding, across darkness and emptiness. And after all of that, those photons landed on a mirror we built, polished by human hands, guided by human intention, and focused into images that we can now look at in comfort from Earth. The improbability of that is staggering. It reminds us that while the cosmos is vast, so too is human creativity, persistence, and imagination. There's also comfort in knowing that we don't have to solve everything. The mysteries Webb reveals may not be resolved in our lifetimes. The puzzles of dark matter, dark energy, early galaxies, and the timeline of the universe may take generations to answer. And that's all right. We are not diminished by leaving questions for those who come after us. We are part of a long chain, each adding a piece, each carrying the story forward. Our vastness lies not only in what we achieve individually, but in what we contribute collectively, across time. For those listening now, in the quiet, perhaps with eyes closed, consider how much has already been achieved by people like you. Ordinary humans, born on a small planet, managed to build a telescope powerful enough to see almost to the beginning of time. That fact alone is a reminder of how much possibility resides within us. If the universe is vast beyond comprehension, then so too is the potential of human beings to explore it, to imagine it, and to find meaning in it. There's a balance here that is important. The vastness of the cosmos humbles us, reminding us that we are not the centre of everything, but the vastness within us elevates us, reminding us that we are capable of reaching out into that immensity and making sense of it. Humility and possibility side by side. Both truths exist together. Sometimes, in everyday life, it's easy to feel trapped in small concerns, the errands, the worries, the endless details that fill our days. But when we look at Webb's images, those concerns shift. They don't disappear, but they take on a different proportion. They become small against the backdrop of billions of galaxies, and in that smallness there is relief. We're reminded that our troubles, though real, are not the whole story. There is more, so much more, beyond them. At the same time, the reminder of vastness can deepen our appreciation for the present moment. If the universe has stretched for nearly 14 billion years, if galaxies have lived and died before our planet was born, then the fact that we exist here and now, able to hear this, to think this, to feel this, is remarkable. Out of all the immensity, we have this moment. That awareness is vast in itself. In the Webb era, this balance of humility and possibility is especially vivid. We see more than ever before, but we also recognise more gaps in our knowledge. We're confronted by both beauty and mystery, by clarity and confusion. To hold all of that together is to hold a vastness that matches the cosmos outside us. We may be small in scale, but we are large in capacity, and so as we bring this journey gently to rest, let's linger with that thought. The universe is vast. It contains galaxies we will never reach, stars we will never touch, mysteries we may never solve. But you too are vast. You contain awareness, curiosity, imagination, and wonder. You are made of atoms forged in ancient stars, connected to the cosmos by every breath and heartbeat. The universe is in you as much as you are in it. That is the gentle reminder Webb has given us, not just of what is out there, but of what is within us. The telescope has shown us galaxies at the edge of time, but it has also shown us ourselves, capable of seeing, capable of wondering, capable of finding comfort in the unknown. And in that reflection, we find a truth both humbling and uplifting. The universe is vast, and so are you. Thank you for spending this time with me, listening to the story of what the James Webb Space Telescope has shown us. I hope these hours of reflection have given you not only knowledge, but also a sense of calm. If you've enjoyed this journey and find it soothing to fall asleep with, you're always welcome to return here whenever you need. If you'd like to hear more stories of science told in this way, you can support the channel by subscribing, liking, or sharing with someone who might also enjoy drifting into sleep with the universe as their companion. But for now, you don't need to think about anything. Just let the quiet carry you. Close your eyes, breathe slowly, and remember, the cosmos is vast, filled with mysteries that stretch far beyond measure, and you are part of that immensity, made of the same ancient stardust, carrying within you the same wonder. Rest well, and until we meet again, may your dreams be as wide as the universe itself,